Hello everyone and welcome to another video. Today I'd like to continue our discussion on root locus. To briefly recap what we talked about last time, we looked at how root locus was really just a fancy term to say where do the poles of a system go as you vary some parameter in the system, right? And this parameter could be anything. But what we decided here is that we're going to focus on a very specific architecture where you have a single input, single output plant, which is augmented by a single proportional feedback controller of magnitude k. And what we were interested in doing now is trying to understand where do the roots of this overall system go as we vary this single parameter k from 0 to positive infinity. What I'd like to do today is look at trying to understand how the root locus is going to change by hand. So we're going to sketch the root locus manually so that we obtain an understanding of how the root locus behaves, as this is going to serve us well in the future when we want to think about designing controllers or compensators using the root locus technique. So to do this, we're going to be taking a look at developing 5 primary rules for sketching a root locus, as well as looking at 5 additional supplemental rules for a total of 10 easy to follow rules for sketching a root locus by hand. So if all of this sounds like more fun than a room full of bubble wrap, let's go ahead and get started. Okay, so this was the architecture we were looking at, where you had a reference input here, an output on this side, the difference in which created an error, that this controller K created a signal U, which went into the plant, which then created the output. So this was the system we were interested in. And again, what we learned from our block diagram algebra discussion was that you could reduce this entire feedback system into a single block. Maybe let's call it T of S, right? With a reference input and just Y as the output. And we saw that this closed loop transfer function, right, T of S, was just given by kg all over 1 plus k g of S, right, for our single input, single output system, right? Okay, so what we want to understand now is, if you think about this long enough, we really want to know where the roots of the closed loop system are, right? I want to understand how the entire system behaves as I vary k from 0 to infinity. So we see that that's just described by the denominator right here, right? This is the characteristic equation of the closed loop system. So why don't we call this maybe delta of S here is 1 plus k times g of S, right? This is the characteristic equation for the entire system, right? Or the closed loop system. So again, I just want to call into attention here the difference between obviously the closed loop system and the open loop system G, okay? All right, so maybe what we should do here is let's look at an example right now of trying to understand where the roots of the closed loop system go, or sketching the root locus for this closed loop system here. And we're going to see here that through the whole discussion now about root locus, the easiest way to get a feel for how these behave is like Nike says, right? It's just do it, right? Just do a whole bunch of these root locuses, and hopefully you'll start to gain some familiarity. So I want to start off with something pretty simple to kind of set the stage of why we might want to understand how to sketch these by hand. So let's look at an example system. Maybe let's call this let's call it G1. Because like I said, we're going to be looking at a whole bunch of different open loop plants. So again, keep in mind here, what we're talking about here is this is the open loop plant G here, right? So this is really the transfer function Y of S over U of S here, right? It's the open loop transfer function. And let's say we got something like this, 1 over S plus 2, okay? So you can go ahead and calculate the closed loop transfer function like we did over there, and we're going to end up with T of S is going to be something like, I think if you do the algebra here, you're going to get k over s squared plus 2s plus k. And obviously the closed loop characteristic equation, or what we call delta of S, is just the the denominator of this, of s squared plus 2s plus k. So we see that obviously that parameter k has weaseled its way into the characteristic equation here. So you can imagine that as you solve k as you change k and then resolve this characteristic equation, you'll get a whole bunch of different solutions for roots of this characteristic equation of the closed loop system. So what I propose here right now is, let's just do something really simple. Let's just go ahead and brute force calculate the root locus. And what I mean by that is, let's go over to Mathematica here in a second and make ourselves a little table here of, basically, we're going to pick some values of k, like, I don't know, how about 0, a half, what else do I use? 1, 2, and 4 here. And then at each one of these k values, let's just go ahead and manually solve the characteristic equation here for the two poles here, okay? So I'll tell you what, let's run over to Mathematica here and do that real quick. All right, so the first thing we're going to want to do here is go ahead and define the open loop transfer function, right? And I think we called that G1 of S. And that was 1 over S plus 2, okay? And then what we can do is define the closed loop transfer function, right? Using the architecture we decided upon here, we said that was G1 of S times K all over 1 plus GK, right? And let's put this together so it looks a little bit nicer. Okay, and then what we can also do is let's go ahead and extract the closed loop characteristic equation, which we called delta, and we said that that was just the denominator of the closed loop transfer function, right? Okay, so here we are. So now what we want to do here is, let's go ahead and use brute force to solve delta of S is equal to 0 for various k values, right? So all we're going to do here is just say solve delta of S is equal to 0, and let's start with k of 0. Solve that thing for S, right? And here we go. So here's one location on the root locus. So when k is equal to 0, here is one valid solution here. Let's also go ahead and maybe let's print this to a number. So instead of using radicals and all that when we get further along, this will print to just a pure numeric number, which will be a little bit more helpful for our purposes. So let's increase this. So let's look at k of a half. Let's look at k of 1. Let's look at k of 2. And let's look at k of 4. And here you go. So you see, here are 5 different solutions for 5 different values of k on the root locus. So we see that as k starts at 0, you start with these poles, but as we start increasing k, the poles of the closed loop system start to move around. And looking at numbers is never very intuitive to me. I like to look at things graphically. So maybe what we should do is we should plot all of these different solutions here on the real imaginary axis. So if we were to do this, let's start off with the k equals 0 term. Here are the poles here denoted as red x's. And then as we increase k to a half, here's the poles here as the blue x's. We keep going up to k equals 1, and they actually seem to meet together there at the coordinate -1, 0. And then as we keep pushing k up, it looks like those poles leave the real axis and they start traveling up vertically. So we see the pattern is the poles start at the red x's, they come together at some meeting point, and then they seem to split off and head vertical. Now, while this is a viable technique for finding the root locus, it doesn't answer the question of why did this occur and what's going to happen next, right? We don't have any physical intuition or understanding or ability to predict, like, do we think maybe if we keep increasing k, maybe the root locus is going to go over to the right half plane? Maybe we just don't know. Maybe the root locus might even turn around and come back and reattach itself to the real axis. So unless we have a better understanding of how the root locus behaves, it's impossible to make these predictions here. So I just wanted to illustrate this numerical technique just to show that, you know what, this is a viable option to find root locus, but it doesn't yield the understanding that we're looking for. So with that being said, let's jump back to the whiteboard and start establishing some of these rules so we can start sketching these things by hand without the need and reliance on numerical techniques. Okay, so let's go ahead and start trying to develop some rules that will help us gain this physical understanding and intuition of how a root locus behaves. So just to remember, here's our closed loop characteristic equation of the entire system. Let's do one thing here. Let's go ahead and break apart our open loop transfer function. So what I mean here is, let's go ahead and write the open loop transfer function. If you remember, it's just a numerator polynomial, let's call it a of s, over a denominator polynomial b of s. Something like this. So again, here, a of s, it's just a polynomial in s, right? And if you remember, the roots of the numerator polynomial basically gives us all of the zeros of the transfer function, right? And then b of s is also just a polynomial in s, but its solutions or its roots give us the poles of the system here, okay? So if I take this and substitute this into our expression of the characteristic equation, substitute it into our expression of the closed loop system, let's go ahead and do that. So let's go ahead and sub into our T of S expression, right? So, okay, T of S is K, G of S we said is a numerator polynomial over denominator polynomial, all over 1 plus K times that same numerator polynomial over denominator polynomial, okay? Now, you do a little bit of algebra, and I'll skip the boring steps here, but if you do this, you can basically write this thing to look like K times A of S all over B of S plus K A of S, okay? So now we see here's an alternative formulation of this characteristic equation of the entire system, this guy, right? So what we see now here is I could also write my characteristic equation of the closed loop system here as basically B of S plus K A of S, right? And again, this is the characteristic equation for the entire or the closed loop system, right? Okay, and naturally what I want to do is look at this is equal to 0 here, right? So the roots of this will tell me where the poles of the closed loop system are. So maybe actually, you know what we maybe should have done here is let's add a little descriptor here. This is not just zeros and poles. Maybe what we should say is this is zeros of open loop system, right? Of just G by itself, right? And then similarly, this is poles of just the open loop system, right? That might be a little bit more clear. So let's go ahead and box this up, because what we're going to basically be doing here is looking at this equation, and this is going to yield a lot of the intuition here, okay? So with that being said, let's go ahead and I'll pause the video, erase the board, and let's start talking about our first rule. Okay, so rule number 1, and I hesitate to almost call this a full-fledged rule. It's almost kind of a duh, yeah, this makes sense here, but basically the number of poles is unchanged. What that basically means here is if you have an open loop system, right? This is your open loop system, right? Maybe let's call it open loop, right? And this thing has n poles, right? And if you remember, the way you got that here is by looking at the B of S, right? Which was, again, our characteristic equation of the open loop system here, right? Is the denominator of the G of S polynomial, right? So this is the order of B of S is basically the number of poles that you have in the system here, okay? Now, what this rule basically states is that when you go ahead and augment it with this type of a control system here, or this type of a block diagram, the one we're interested in, like this thing will still have n poles, okay? So adding this control feedback doesn't add any extra poles to the system here, okay? So let's see how we can prove that to ourselves to make sure that this is actually the case here, right? So again, the reason that we're going to be able to see this here is, again, go back to our breakdown here where we said G of S was a numerator polynomial over a denominator polynomial, all right? And we saw that basically the order of A of S, right? This is the number of zeros, right? And similarly, we said the order of B of S is, let's call that number n here, and this is the number of poles, okay? Now, let's go ahead and make the assumption here. Well, actually, you technically don't have to. Well, I guess we do to make this reasonable here. But let's go ahead and assume the system is proper, meaning n is greater than or equal to m. So you have more poles than you have zeros, or the same number here, right? So basically the order of the denominator is greater or equal to the order of the numerator here, right? Okay, so if that's true here, let's go ahead and look at what is the closed loop characteristic equation of this thing here, right? By the time you augment it with this kind of interesting architecture, how many poles are there? Well, remember we said that, okay, that is given by the characteristic equation, delta of S, which we had just said is basically B of S plus K A of S, right? So if you look at this expression long enough, you see that this is basically a polynomial in S. Of what order? Well, we said that, sorry, did I switch this here? No, I think I got that right. Right, it's of order m here, right? Because there's m0. So this is polynomial in S, and basically we should say order m, right? This k in front of it is not going to change the order of this polynomial, right? It's just going to multiply all the coefficients by k, right? This guy over here, this is also a polynomial in S, and this thing is of order n, right? So if you look at this long enough, right, you see it's basically a polynomial of order n plus a polynomial of order m. The only thing that's going to happen is you're going to get another polynomial whose order is either the maximum of n or m, right? And since we assumed that the system is proper and we said that n is greater than or equal to m, we see that this whole thing, we can say, has something like an s to the n as the highest power. Right? So in other words, what we see is the closed loop characteristic equation of this entire system still has n poles in it here, right? So we see that you haven't changed the number of poles here, right? This here is the number of, and again, I keep dropping off the, maybe what we should have added in here was open loop here, right, as another descriptor here, right? Because m is the number of open loop pole zeros, n is the number of open loop poles, and that doesn't change when you close the loop with this structure here, right? So basically, we have the exact same number of poles before and after adding this control system onto it, right? So if you want a quick example here, feel free to run this example yourself if you really want to convince yourself here. Let's choose like a G2 of S, right? Some other open loop transfer function that looks like a 2s squared plus 3s plus 4 all over 5s cubed plus 2s squared plus 3. Okay, so again, the top numerator is my a of s, the bottom denominator polynomial is what I called b of s. So we said that for the entire system, right, which was basically the closed loop system, we said the characteristic equation for that was, where was it? Didn't we just have it written down here? Oh, right, yeah, right here, right? This is b of s plus k times a of s, right? So just plug in your b and your a, you know, run over to Mathematica, do the algebra, and I'll spare you the boring manipulations of algebra. And what you'd basically get here is this is going to be 5s cubed plus 2 plus 2ks squared plus 3ks plus 4k plus 3. Okay, so again, we see that the open loop system had 3 poles here, right? You can see from the denominator here that there's 3 poles and 2 zeros. Okay, well, the closed loop system is still a third order polynomial, so this is still going to yield 3 poles. So again, rule number 1 just states that if you start out with n poles, after you close the loop with this type of an architecture, you will still have n poles here. Okay, so again, it's almost one of these things that, yeah, sure, that makes perfectly good sense. I don't know why we needed to spend, you know, 5-10 minutes talking about it, but it will help when we come here and look at our drawing our root locus. It basically says that none of these poles are going to disappear and no poles are going to magically reappear here. Okay, so we got to keep that in mind. The number of poles is unchanged here under this type of an architecture here. Okay, so let's pause the video. I'll erase the board and we'll move on to rule number 2. Okay, moving on to rule 2. And rule 2 states that closed loop poles start at open loop poles and go to open loop zeros. And maybe we're going to put a little asterisk up there here. So, wow, that's actually kind of a long title for a rule here, but let's go and see what this actually means here. So, to see this, again, let's go ahead and consider the closed loop characteristic equation of the entire system, right? So, it was this. Okay? And again, to refresh your memory, right, the architecture that went along with this here is, you're going to see us drawing this a couple of times tonight here, so hopefully you're going to get very comfortable with this. Was that, okay? So let's go ahead and examine this here. So we can make the immediate observation here that, note, what happens if k equals 0 here, right? If k equals 0, let's plug this in here. So if k equals 0, the closed loop characteristic equation here for the overall system just becomes b of s is equal to 0, right? And if you remember, b of s, this was the characteristic equation of the open loop system, right? So its solution yielded the poles of the open loop system. So what we see here is that when k is equal to 0, the poles of the closed loop system are equal to the poles of the open loop system. So that's what we're talking about with the first part of this rule here. So it actually makes physically good sense if you think about this here, right? If k is equal to 0, it's like this controller is not even working at all, right? It does nothing here, right? So the only dynamics that are still remaining in this system here are the dynamics introduced by the original system here. So we see that at k equals 0, that's basically like saying the controller is not doing anything. It's an open loop system here, so it behaves like an open loop system. So great. We see that when k is equal to 0, the poles are at the open loop locations. This basically tells us that since our root locus, we're interested in understanding where the roots go as k goes from 0 to infinity. We see that the root locus, it starts when k equals 0 at the system's open loop poles here, right? Okay, great. Let's go ahead and examine the other extreme here. So what about when k tends towards positive infinity here, right? Well, again, look at our expression for the characteristic equation here. It's b of s plus k times a of s is equal to 0, right? So as k starts getting bigger and bigger and bigger, right, this term starts to dominate, right? Because this it's going to start swamping out. I don't care what b of s is, whatever order it is, right? This is going to start swamping the solution. So we basically get that your closed loop characteristic equation at large k effectively looks like k times a of s is equal to 0 here, right? And now in this case, k is huge, so I can divide it through here. So we basically get here that the characteristic equation is effectively something like this. Okay, so again, if you remember, what was a of s? A of s was basically the numerator polynomial of the open loop system, right? And if you remember, right, solving its characteristic, or sorry, solving this polynomial equal to 0 yielded the open loop zeros. So what we see over here is, again, delta of s, this is the poles of the closed loop system at large k are approximately equal to the zeros of the open loop system here, right? Let's go through an example of this here just to convince ourselves that this is true here, okay? So let's go ahead and pick a example system here. Where's my example? Oh, here, okay. Let's pick some transfer function, some open loop transfer function, G3 here in this case. So I'm going to use an example of, here, I don't know, s plus 1 plus 2i, and then s plus 1 minus 2i as a numerator here, and the denominator of s plus 2 and s minus 3 here, right? Okay, Again, this is going to be A on the top here. This is A of S. And the denominator is what we were calling B of S here, right? So let's make a couple of observations of the open loop system. In other words, let's look at the open loop poles and zeros, right? So we can immediately see that what? There are zeros at S is equal to what? -1 minus 2i, and S is equal to -1 plus 2i, right? That's the roots of the numerator. And then we have poles at S is equal to -2 and S is equal to +3, right? These are the open loop poles here, right? So again, I guess if you really want to be explicit, right? Again, these are open loop zeros and open loop poles, right? So now what we want to go ahead and do is let's go ahead and formulate delta of S here, right? So the closed loop system, its characteristic equation here, again, at the risk of being overly repetitive, let's just write down the characteristic equation here again. So it's B of S, which is going to be S plus 2, S minus 3, plus K times the quantity S plus 1 plus 2i, S plus 1 minus 2i. Right? So here's my closed loop characteristic equation. I want to solve this thing equal to 0. So again, let's run over to Mathematica here and solve this thing for a whole bunch of varying different k's, starting low, going to high, and see, do the poles, do the roots of the closed loop characteristic equation, they should start here, and then they should eventually move to this location as k gets larger. Okay, so let's pause the camera, run over to Mathematica, and make sure that's the case.
All right, here we are in Mathematica, and for ease of reference, I've just transcribed some of the stuff we had on the whiteboard here to the notebook. So you can see that we've got ourselves the open loop system with the open loop zeros and open loop poles as we discussed, and the closed loop characteristic equation for the system was given by this. So let's go ahead and make a function for this, and actually let's make it a function of both S and K here, because we're going to want to be varying K here in a second here to see how the solutions to this changes. Okay, so let's just go ahead and type in the characteristic equation. And now all we want to do here is solve this for various k values. So let's just go ahead and start with k of 0 here. Let's solve this thing equal to 0 for S. Whoops, like that. There we go. And here we go. And we see, yes, this makes perfectly good sense. We see that at k equals 0, the poles of the closed loop system are actually the poles of the open loop system. So that makes perfectly good sense. Let's just go ahead and start increasing this here. So let's go ahead and say, how about, I don't know, k of 1. Okay, and we get something different. And you know what, before we get too far down this road, let's print all these to a number just so we don't have to deal with all these radicals and square roots and all that kind of stuff. Okay, so here we go. We see the poles are moving, and as we keep increasing k, let's start going up by orders of magnitude. How about let's go 10, and then maybe how about 100 and 1,000 here. So we're increasing k by orders of magnitude here. Okay, and you see what's going on. Shucks, looks like it's not all on the same page here. Tell you what, let me copy and paste this here. Whoops, sorry, not cut. I want to copy, and let's paste this down below just so we can see. So again, we see that when k is low, the system's closed loop poles start at the open loop poles, but when k is high, the system's closed loop poles start to approach the open loop zeros. So that's actually pretty interesting. You know what we should do, though, is let's refine this further, because if you think about this in combination with our previous rule, so let's just write down, if you recall rule 1, right, this stated that the number of poles does not change. So you might be wondering what's going to happen here if there were a different number of poles and zeros, right? So for example, let's go ahead and augment our example here. Like, what if there were more poles than zeros here? Okay, so for example, what I want to say is let's augment this thing with an open loop pole of, how about S at -5? So I'll put an S plus 5 here, right? So now what we need to do is let's redo our list here of. We're going to have to update all of this, right? So let's copy all this, come down here, paste below. So the open loop zeros stay the same, right? We still only have 2 open loop zeros, but now there's actually 3 open loop poles. Sorry, -5, there we go, right? So let's change the characteristic equation. This should now be s plus 5, right? So this is a little bit interesting here. So let's go ahead and redo our analysis. Let's redefine our characteristic equation. Oops, sorry, let me delete some of this. Okay, so now with the added pole, this is s plus 5. And we can do this again. So let's shift enter that, and then I'm going to shift enter this to solve again. And now, again, this all didn't fit in one page, so I apologize. Let me copy all of this stuff and then paste it down below so we can compare the results. And we see here, again, when k is 0, right? When k is small, again, we have the exact same result we had before, right? The closed loop poles start at the open loop pole locations here, right? But now, this is fascinating. As k gets bigger and bigger and bigger here, right? Rule number 1 stated that these poles just don't disappear here, right? There's always going to have to be 3 poles, but there's only 2 zeros for them to go to. So what ends up happening is, if you look at this here, is 2 of those poles will end up going towards 2 of those open loop zeros here. So these 2 closed loop poles that I've highlighted here in blue are going toward the open loop zeros here. And that third pole here, right, well, it can't just disappear. So what it's doing here is it actually appears like it's shooting off to infinity here. This is sometimes referred to as a 0 at infinity here. And one way I heard this really well explained, if you guys haven't found Brian Douglas's channel, Brian Douglas is kind of the king of YouTube control videos. I'll link to his his videos in the description of this video. But he kind of said that, you know, poles and zeros, they're sort of like these happy friends. They always want to find one another here in the root locus. So these open loop poles either need to go to an open loop 0, or they need to go to one of these open these zeros at infinity are what these ones are called. Right? So this is fascinating. Why don't we go ahead and run over to the whiteboard and write down a consents form of rule number 2.
All right, so combining all of this analysis, we can basically write down rule 2, which we said is has this nice long title, but we basically see now that the way we can concisely write this down is we can say that the root locus starts, right? This means start means k equals 0 here, right? So it starts at open loop poles. Right? Let me erase some of this to get ourselves a little bit more real estate. And now that's where the root locus starts, and we just saw here that the root locus ends. Basically, this is when k is infinity, right? It ends at one of 2 locations. So it either ends at A, it ends at open loop zeros. So we saw that the same number of poles that there are zeros, each open loop 0 will attract one of these open loop poles. So in other words, m poles go here. So again, remember, m was the order of the numerator, or the number of open loop zeros there were here, right? So m of those open loop poles will go to these open loop zeros. The other option here is that they either end at zeros at infinity. Right? So you have the remaining n minus m poles go here. So again, box this up. Here's our concise way to understand rule number 2. So again, to conceptualize this, or to summarize, the root locus starts at the open loop poles, and then as you increase k, as k gets larger and larger and larger, some of those open loop poles are going to get attracted to these open loop zeros. The remaining poles that don't have this nice happy buddy friend, as Brian Douglas puts it, will go to these zeros at infinity far away here. So before we leave this here, maybe let's just make a quick small note here, and I want you to file this in the back of your head, because we're going to come back to this and it'll be helpful when we're designing compensators and controllers based on this. If you think about the ramifications of rule number 2 here, you can think that zeros, whoops, let me see. These open loop zeros, they sort of act like magnets for the root locus. Because you can clearly see right here, as you start increasing the gain here, these zeros will start attracting, or the root locus will start going towards these open loop zeros here. So when we start designing things like PID controllers using the root locus technique, you're going to be able to leverage this fact here by, if you place the zeros appropriately, you can use it to sort of attract or suck in the poles to those locations here. So again, I just wanted to throw that in here so you can think of, I like to think of zeros in the root locus as sort of like magnets here for my root locus. Okay, all right, so let's go ahead and pause the video. I'll erase the board and we'll get on to rule number 3. All right, so like a bus coming down a mountain with no brakes, let's keep rolling onto rule 3. And this is, again, a bit of a mouthful here, but it's very powerful here. So this basically states here that valid regions on real axis are to the left of odd numbered poles / zeros. This is when you start numbering from right to left. And again, yikes, that is a large title here, but very descriptive, I feel. So let's take a look at what this actually means here and how we're going to derive this here. So before we jump into this, just recall here, let's talk a little bit about a complex number here. So if you have z as being a complex number, right? If you remember, the way we understood this here is you could think of this as like an alpha plus a beta j here, right? So there's a graphical representation here that this imaginary number z here might have some alpha real part and some beta j imaginary part. But the other way you can think of this, right, is we could have thought about an imaginary number z as being a vector in this plane here, right, with an x component and a y component. We showed here earlier in one of our earlier discussions here that you could use Euler's formula to also represent this vector z here, or this complex number z here. So let's just say that you can use Euler's formula to write z here as basically the magnitude of that complex, of this vector, right, times an angle here, or you could write this here as e to the I theta here, right? Where theta was the angle associated with this complex number here, right? So this here was theta, right? And here was the magnitude of the complex number, right? So this was Euler's formulation, and it was an alternative representation to this sort of Cartesian representation of a complex number, right? Okay, so using this here, let's go ahead and examine what's the quotient and the product of two imaginary numbers here. So, for example here, let's look at here a quotient of two complex numbers. And let's call these two complex numbers u and v. Okay, so in other words, I want to examine what is u over v here, right? Okay, so again, we can use Euler's formula to write u as magnitude of u times e to the I, let's call it theta u, right? There's some angle associated with u, divided by v, which is now magnitude v e to the I theta v, right? Which you can actually write this here if you remember our rules of exponents here, right? This is magnitude u over magnitude v, right? Let's maybe put this in parentheses, right? As a big giant magnitude here, right? Times e to the I, and then this would be theta u minus theta v here, right? Okay, and in a similar fashion, we can examine the product of two complex numbers. Again, let's use u and v as our descriptor. So I want to look at u times v. So again, that's magnitude u e to the I theta u times v, which is magnitude v e to the I theta v, which again, let's just group the magnitudes as magnitude u times magnitude v times e to the I theta u plus theta v, right? So what we end up seeing here is that this angle here, right, this is the angle of the quotient here, right? So this is basically, well, I guess how should we write this here so it's not complicated here, right? But this is effectively angle of quotient, right? And here's angle of product, right? And I guess you can see the same thing here. Here's the magnitude of the quotient, and right, and this is the magnitude of the product, right? So in other words here, right, what we can write down here is that the angle of u over v here, right, this entire thing, maybe we should be very explicit here, right? Maybe we should put this in parentheses, right? If all I care about is the angle of the quotient here, we see that, all right, that is just the difference of the two angles of those two numbers, right? This is angle of u minus angle of v, right? And similarly, the angle of u times v, right? If I want to know what is the angle associated with the product of two complex numbers, we see it's just the addition of the two individual angles, right? So this is angle of u plus angle of v, right? These are going to be the key results that we are going to use here in the future, but you know, just in the interest of completeness here, right? I guess you could also say here, if we're breaking down these two complex numbers, just as a nice sidebar, if you want the magnitude of u over v, right? Again, we see here that it's just the individual magnitudes here, right? So this is magnitude of u over magnitude of v, right? And then the product here, or the magnitude of the product of two complex numbers, it's just magnitude of u times magnitude of v here, right? So again, these two other results that deal with the magnitude are not as important here as the angle for our discussion of root locus. So let's see why that is the case, okay? So let's go ahead and I'll erase this because this is not as important here. Let's keep up our result of the angle so we can apply that here in a second. Let's go ahead now and go back to our open loop transfer function, or you know what, actually this is applicable for any transfer function. So consider here a general open loop transfer function. So again, we were using g of s to denote the open loop transfer function here. And again, what this could look like here, it's just a polynomial numerator over a polynomial denominator here. So it's a bunch of zeros and a bunch of poles here, right? So let's just make this like a s plus z1, s plus z2, yada, 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 all the way s plus zm, right? And then you could have down here, you could have s plus p1, s plus p2, yada, 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 all the way s plus pn, all right? And you might also have an arbitrary gain to this here. Let's use the gain alpha here, right? I don't want to use k because we're reserving k for our parameter we're varying in our root locus. So again, alpha here is just a constant gain, okay? Okay, so, all right. Again, this numerator here, we said we also call this a of s, right? And then the denominator, whoops, I missed a parenthesis there. Denominator was called b of s, right? Okay, so we know here that, let me see here. We showed earlier, right, that the closed loop characteristic equation, right, under the feedback or the structure that we talked about, right, like this, right, the closed loop characteristic equation of this system here was given by, tell you what, let's come over here. We're going to need a little bit of space here to write this out. So let's clean off this part of the whiteboard and write down the closed loop characteristic equation, which we call the delta here, right? We said that this is that delta of s, right, is b of s plus k a of s, right? Okay, so substituting in here, here's our a in the numerator and the b of s down here. Let's just substitute this in. So b of s here is just our s plus p1 plus p2 all the way down to s plus pn, right? Plus k times the numerator, which is a of s, right? K alpha s plus z1, s plus z2, s plus zm is equal to 0, right? Okay, let's rewrite this here. So Let's see. I want to get this thing to look like, let me see. Let's move this over to the other side. So well, tell you what, let's not skip any steps. Let's keep this explicit. So we can write this as, let's get the left side. S plus P1, S plus P2, S plus Pn is equal to, I'm going to move that to the other side. I get minus K alpha S plus Z1, S plus Z2, S plus Zm, right? Okay, now let's divide K to the other side, and also I'll move this to, well, you know, again, maybe let's not, I always want to skip steps here to make this go a little bit faster, but maybe in the interest of making this explicitly clear, let's do this step by step here. So what I want to do here, let's divide through by minus K. Okay, now I got alpha S plus Z1, S plus Z2, S plus Zm. Okay, now let's divide this numerator, which was really B of S, and move it down to the other side. So all I'm left with here on the other side is minus 1 over K is equal to alpha S plus Z1, S plus Z2, S, oops, should be an S, excuse me, S plus Zm all over S plus P1, S plus P2, S plus Pn. Okay, great. So what we see here is again, this is just another way to represent our closed loop characteristic equation here, right? And if you look at this long enough, it's a complex number, right? The right hand side, S is a complex variable. These poles and zeros, they could be complex variables. So this is basically a complex number equation, right? Now, what we want to do here is let's go ahead and just realize. So first write down, we realize these are complex numbers. Okay, so now let's just consider the angle of this complex number. In other words, all I care about is, let's look at the angle of the left-hand side. It's got to equal the angle of the entire right-hand side. Maybe let me put this in big parentheses here, because I'm just doing an angle operation on the entire thing. And hopefully something is going click in your head now, and you kind of see why this might be related to our Euler discussion we just had, right? Because if you look at this long enough, let's think about this. Now, the left-hand side, this is actually really easy to deal with, right? If you think about this, what did we do with K? So if you recall, right, for our root locus, we are going to consider K in the range of 0 to positive infinity here, right? So K is the parameter you're varying. It's a real number, right? It's a gain here in your compensator. You're not going to use imaginary numbers here, right? That would make no sense to have an imaginary controller. This is going to be a real number that varies between 0 and positive infinity here, right? So this left-hand side, if you think about this long enough, what this looks like for any value of K in this region is you basically end up with what? If you were to plot this on the real imaginary axis, it's something like this, right? It's only in this region, right? As K goes between 0 and minus infinity, the term negative 1 over K looks like this. So this dark dashed black line is minus 1 over K, right? So the angle associated with this for any value of K, you can see it's basically pi. Or I guess minus pi, however you want to think about it. It's some 2 pi multiple of 180 degrees. Sorry, I mixed degrees and radians there. You get what I'm saying here, right? It's basically pi or negative pi plus or minus 2 pi k. So this whole left side, this basically boils down to, let's do minus pi. It's the same thing, right? Plus or minus 2 pi k. And I apologize for having now lowercase and uppercase k. So lowercase k is just some integer here, right? So you can wrap around 2 pi or negative 2 pi or 4 pi, 6 pi. It doesn't really matter here, okay? So the left side you can basically see, you can think about it as just 180 degrees or negative 180 degrees or some multiple of it, right? Now, the right-hand side is where it gets interesting here. And basically, you see that this right-hand side is a whole bunch of products of complex numbers and quotients of complex numbers. So we're just going to use Euler's expression right up there to simplify this entire left-hand side, or sorry, right-hand side, okay? Let me keep up Euler's expression because we're going to use this quite a lot here, okay? So let's just break out the whole the entire right hand side. So we see that the left hand side we said was basically minus pi plus or minus 2 pi k, and now the right hand side we basically get what? It's angle of alpha plus angle of s plus z1 plus angle of s plus z2 plus da 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 angle of s plus zm, right? And then since these are down in the denominator, right, or the quotients, we're basically going to subtract off them, right? So then it's minus angle of s plus p1 minus angle of s plus p2 minus yada 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 all the way up to angle of s plus p n. Right? Okay, so great. Let's look at each term. Let's look at alpha here, right? If you remember, what was alpha? Alpha was like the constant gain in the transfer function here. Let's go ahead and assume that alpha is positive here, right? So let's go ahead and say assume alpha is greater than 0, right? So again, what is alpha if alpha is greater, or sorry, what is the angle of a positive number, a positive real number? Well, it's the exact opposite of this, right? It's just going in the other direction. So the angle is 0 here, right? So I think everyone would agree that this is just a big fat 0. Okay? And then if you look at this, we actually end up with a major result. All these are, you see, we're just adding. This is the cumulative sum of all of the angles of these s plus zeros. So in other words, what I'm getting at here is the right-hand side. I think all of these terms that I'm kind of bracketing right here, right? Wouldn't maybe an easier way to write that would be summation from I equals 1 to m of the angle of s plus zi, right? And then all of these down here, you see, are basically another summation, but it's just the angle of the poles here, right? But I got to stick a minus sign here, right? So this is minus summation I equals 1 to n of angle of s plus pi, right? And then again, this equals minus pi plus or minus 2 pi k here. And again here, where k is in the integers here, right? Sometimes people write as a scripty z or a natural number here, but this is basically, k is just an integer value, right? This is an incredibly important result here for our root locus, so we better just box this up here. And you see that all it deals with is the angle of the pole, the cumulative angle of all of these zeros, cumulative angle for all of these poles. And we're going to have to take a closer look at this. But I want to stress how important this is because we're going to use this for the next several rules. And this is key to understanding the root locus is basically this result here, which we see is nothing more than an angle formula looking at complex numbers. So in fact, this result is so popular and so important that we're going to have to write it a couple of times during this discussion. So I actually went ahead and I made... It's so important to me that I even made a little thing here, right? So that we can pull up every once in a while. And I'm sorry, I flip-flopped the result here, but this is the result, right? This is I kind of want to get this framed and hang it above my bedside. We're going to be using this quite a bit here. So let's see how this can maybe apply now to our rule number 3 here, okay? So the first thing we should maybe ask ourselves, now that we've got this result here, is we got to ask ourselves, what the heck are all these terms like? What is angle of s plus z1, angle of s plus z2, Heck, what does it mean to have an angle of a complex variable plus a complex number here, right? Where does this live in the real imaginary axis? So to answer that question, let's erase some space over here and think about drawing out a clean real imaginary axis and try to label some of these terms here, okay? Okay, so let's first draw ourselves, we'll tell you what, first let's write down, let's consider a term. How about s plus zk, some zero here, okay? So what I'm looking for is, we're trying to look at what is this thing, s plus zk, angle of that complex number, right? What is that, okay? So to understand this a little bit better, let's go ahead and draw a real imaginary axis as sort of cleanly as I can. Okay, and let's start with a simple case. Let's start with the case of maybe like a real zk here, okay? So maybe in the back of your mind, if you want to think of this like as something like what is angle of s plus, I don't know, 3? Let's assume, how about maybe that zk is 3, okay? So that means in the numerator you have something that looks like an s plus 3, which implies you have what? You have a 0 at minus 3 here, right? So 1, 2, minus 3, right? So you would have this 0 right here. Would everyone agree? So this here is minus 3, or I guess you could also write minus zk. Right? That seems reasonable, okay? So again, you got to remember that these are complex numbers, so you could also think about them as vectors here, right? We showed earlier that you can either use Euler's formula to think about them as sort of as a magnitude and angle here, or the Cartesian representation. But let's ask, where is this vector zk? What if I consider just this term zk to be a vector? Well, I think you would all agree that if this here is minus zk, wouldn't a vector, if I drew it, I started it right here at the 0 location, and I draw it to the origin, like this is the vector zk. Maybe I'll put a bar on top to denote that it's a vector here, right? That seems reasonable. Okay, now we got to ask, what is this s term, right? S, you remember, is just some location in the complex plane here, right? It's a location I'd like to consider here. So I don't know. Let's pick something. I'm gonna use green here, and I'll maybe put a little dot here or something like that here. This here is like the point S that I'm considering, right? So if that's the point S, remember we talked about this can be considered a vector. So the vector representation of S would be from the origin out to the vector, like this. And I'll try to make this a little bit thicker. I know the green is a little bit hard sometimes to show up here. So I think everyone would agree that this green vector is S. And again, I'll put the little bar on top of it to denote a vector, right? Okay, so if we're talking about vectors then, you can add two vectors. Here's the vector zk, here's the vector s. So if I add the two here, that's here to here, right? This is the vector s plus zk, right? Maybe I'll put a vector on top of it to denote that, right? So now that we've got this makes a lot of sense, because if I want to know what is the angle of s plus zk here, right? I just need to look at the vector, and I need to look at the angle that vector makes with the horizontal. So here's the angle right here, right? So this term right here, or this, is basically angle of s plus zk, right? And this analysis holds similarly if what if zk, you might be asking, oh yeah, maybe this was only for a real axis result. What if it was imaginary? It's the same picture here. It's the same result. Just to convince yourself of that, tell you what, let's erase some of this and maybe redraw it right next to it here. Here's our real, here's our imaginary. Okay, so now, you know, what if zk was imaginary, right? So you would still have a pole out here, or sorry, excuse me, a 0 here. This is minus zk, right? So the vector is still going from the 0 location to the origin. This is the vector positive, or zk, right? And then you want to go ahead and consider yourself some s point somewhere else, right? You still got the vector going from the origin to that point here to be a vector version of s, right? So then I can still add the two together here, and you end up with this being s plus zk, right? And the angle then is still just what that angle makes from the horizontal, or sorry, what that vector makes from the horizontal. So this is angle of s plus zk, right? So if you look at this, we see that now if you want to evaluate these terms, angle of s plus zk or angle of s plus pk, right? And there's no difference if this was a 0 or a pole here, right? The whole same process still holds, right? You still draw all these vectors and measure the angles. So the procedure here to get angle of s plus, and again, I'm just going to use zk as a representative, but this could still be pk, it could be whatever, right? It's just the angle of this funny vector here. So the procedure here is, step 1 here is plot location of the 0, right, at minus zk, right? You got to remember here that the actual location of where you plot the 0 is at negative zk, right? Because you're looking for the value of s that makes this term 0, right? Okay, so step 1 is you plot that location in the s-plane at negative zk, right? Then the next thing what you're going to do here is you would then plot the location of a candidate S location you would like to investigate. Or consider, or what have you, right? Just pick some point in the S-plane that you're interested in. Then step 3 is all you're going to do then is you're going to draw a vector from your candidate S point to the location negative zk here, right? Or to the location of that 0, right? So next here, step 3 is draw a vector from, oh, excuse me, I might have said, wait a second, did I say that backwards? Hold on, back up. I did this wrong here. Sorry everyone, I drew this completely, I went too fast, got too caught up in the moment. It's backwards, right? I got the direction of the vector backwards, so I screwed it. Sorry guys, I royally screwed this up. Sorry. It's the other way, right? If I'm doing vector addition correctly, this is s, yeah, plus zk. Yeah, it's from the pole to the s location. Yeah, because this is the vector s, this is the vector zk, so this is zk plus s. Yeah, yep. See, right, I got the direction of the arrow completely wrong, which will now change the angle, right? So now this is the angle. It's over pi, right? This is angle s plus zk. Whoops. Sorry, everyone. Yeah. Okay. But sorry, let's get back on track. This is where I caught myself, right? Because number 3, step 3 here is you draw the vector from the 0 location at minus zk to the candidate point you're interested in, right? So draw a vector from minus zk to s, right? And this is the vector s plus zk, right? And maybe again, let's put the bar on top of that, just to denote that that's the vector that you're going to draw, okay? And then lastly, step 4 is once you've got that vector, right, you can easily compute the angle of s plus zk, right, by just measuring the angle from the horizontal. By measuring the angle from horizontal to the vector s plus zk, right? as we saw over there, okay? So it's easy. It's not an Alcoholics Anonymous 12-step program. It's only a 4-step program, right? So this is actually really, really simple. And again, this is so important here that we're gonna be using this a couple of times. I again made ourselves a little handy dandy little cheat sheet here that we can hopefully pull up every once in a while. And here's the four steps, right? Just plot the location of the 0 or pole at negative zk. Plot the location of the candidate S point that you're interested in investigating here, and then draw a vector from minus zk to S, so you get this blue vector here, and then just compute the angle by measuring the angle from horizontal, right? So there you go. Okay, so we now know how to understand all of those terms in equation 10 here, right? Remember we said, sorry, in my notes I call it equation 10. I guess I never really labeled it, but this is the root locus angle plot. So we see all you're doing here is you're adding all these angles that are contributing from the zeros and subtracting all of the angles that are contributed by the poles, and that better equal some multiple of pi here, right, in order for it to satisfy the root locus, okay? So the way to think about this is, in order for a point to be a solution to the closed loop characteristic equation, it has to satisfy this angle expression here, right? Okay, so let's get back on track now and ask ourselves, how is this related to our rule number 3 here? Okay, so to do that, let me tell you what. Let me pause the camera, pull all this off, erase the board, and get a little bit of space so we can run through an example. Okay, so what I want to do right now is let's draw ourselves a real imaginary axis. Okay. And now what I would like to do is look at a couple of cases here. So first, let's only consider S locations on the real axis. Okay? And now, if we're considering only this, let's consider 2 sort of sub cases here. So let's think about having maybe a zk on the real axis. And let's think about having a zk as part of a conjugate pair, or a complex conjugate pair. Okay, so let's start with this first case here. Okay, so what I mean by that here is, okay, you've just got something here, right? Here's your minus zk, or here's the location of one of these zeros. Okay, now, remember, maybe let's go ahead and pull up our little procedure here. I'll tack this up on the far side of the board so we can kind of remember how we can go ahead and measuring all these angles, right? What I want to think about now is candidate S locations that are only, right, we're only going to consider things on the real axis. So like right here, here's S. Okay? So we see now that what we're looking for is, what is angle of S plus zk, right, is equal to something. I don't know, right? Now, the way we get to get that angle is we use our little 4-step process here, right? So all I got to do now is draw a vector, right, from zk to S. That's this, right? And then I measure the angle. So in this case, what's the angle? It's super easy. It's horizontal. The angle's 0, right? What happens if I move S to over here? Doesn't change. It's still 0. Still 0. 0, 0, 0, 0. Until, what happens when you start considering S's on the other side of this? Now this is the S location, right? So again, I follow our little 4-step process here, and I draw a vector from the 0 to the candidate point in question. And now I look at the angle. So, aha, this is interesting. The angle now flips to 180, right? Because now, here's angle of S plus zk, right? So here, this is actually pretty interesting here. So in case A here, angle of S plus zk, it's only 2 values it can possibly take here, right? It's 0 if S is to the right of negative zk, which is basically the 0 location, right? And it is what? It's pi otherwise. Or I guess the otherwise is, you can think about it, is if S is to the left of minus zk, which is the 0 location, right? So again, this was for case A. Let's now switch and ask ourselves, what about in case B here? What if instead your picture was, let me redraw this as quickly as I can here. Okay. You had like a complex one, minus zk. Something like that. And remember, we know that zeros and poles and any complex, they come in conjugate pairs, right? There's another one down here, right? Okay? So now what we can do is, we're going to do the same thing. We're only going to consider S locations on the real axis. So again, look at this. Here's the S that I'm interested in, right? So if I'm looking for the angle that's associated with this pole here, we can follow our 4-step process here, and I draw a location from here to the S location, and then I measure the angle. So here's the angle. Here's angle of S plus zk. Right? And you see it's not 0, and it's not this nice pi or anything like that. But what's fascinating here is if you consider now angle of S plus zk, right? We said that this was, you can see right here, it's going to be some weird number depending on where it's located here, right? But if you consider the angle of S plus zk plus the angle of maybe zk tilde, which is its conjugate pair, right? So that's the one down here. This is minus zk tilde, right? That's its sister pair. Let's look at what is the sum of these two things put together. Right? So let's get angle of S plus zk tilde. Well, same deal. I just draw a location from zk, negative zk tilde to this S, right? And here is this angle, right? Here's angle of S zk tilde. And you can see by symmetry here, if S only moves its way along the real axis, this stays at 0 all the time, because whatever angle this top 0 contributes, you get exactly the opposite angle from the bottom here, right? So this is fascinating. This is a big fat 0 all the time. It doesn't matter where on the real axis you move this green S dot. It's due to symmetry, it's always 0. Right? So that's really awesome. And again, all of this analysis is the same if these were poles, right? If I had drawn just a red X instead of a red O, it'd be the exact same story here, right? So we can take these two things to the bank here with us and think about using this to generate our rule number 3, okay? All right, so to generate rule number 3 here, let's look at a slightly more complicated transfer function here. So maybe what we'll do here is, yeah, let me go ahead and erase this, and I'll write up the transfer function. Okay. Okay, so let's look at an example here. This is going to be a little bit more complex here. Let's call it, I think, G4. Maybe we're onto our 4th unique transfer function that we're examining here. So this is going to be something like S plus 1 plus 2i, S plus 1 minus 2i, S plus 3 in the numerator, all over a S plus 2, S minus 2, S minus 4, right? So again, I guess if you want to write this in our little S plus Z1, S plus Z2, S plus Z3, we see there are 3 open loop zeros, and there are S plus P1, S plus P2, S plus P3. There are 3 open loop poles here, okay? So what we can do here is let's plot on our, let's make a real and a imaginary axis here. And let's quickly just do a pole 0 map of where all these poles and zeros are located here. So let me see. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 1, 2. Okay. So let me see here. Okay, let's just deal with, how about the poles first here. So we got a pole here at -2 here. So here's a pole. This here is minus P1, right? Which is -2, okay? Then we have another pole here at +2 here, right? This is minus P2, which is actually +2, right? And then finally we got a pole here at 4. So here's minus P3, which is the same thing as 4, right? Okay, now let's deal with the zeros. So here's Z1 here. This is at -1, -2i down here, okay? So here is negative Z1, which is the coordinate -1, -2i, okay? And then we got another 0 up here. It's conjugate pair, right? This is minus Z2 at -1 + 2i. And finally, we got a 0 over here. This is minus Z3 at -3. Right? Okay, so there's our pole zero map of the open loop system here, okay? And now we got to ask ourselves, again, remember, we are only considering the real axis, right? Rule number 3 only deals with the real axis. We got to ask ourselves, which locations here satisfy equation 10? And sorry, again, I keep calling it equation 10 because that's what I have in the notes here, but let's slap it up here. Here is our mega, do I have enough room for this here? Well, let's put it down here, right? This was our important expression here, right? This governs which locations in your real imaginary axis. In order for it to be on the root locus, it has to be, it has to satisfy this expression here, right? So let's expand out this equation for our particular case here, right? So to do that, let me just maybe write it, tell you what, let's write it right underneath of this here, okay? So this expression, I need to sum from I equals 1 up to the number of zeros, so that's 3. So I got angle of S plus Z1 plus angle of S plus Z2 plus angle of S plus Z3, right? Okay, this minus, I got to take all the angles associated with the poles, right? Minus angle of S plus P1 minus angle of S plus P2 minus angle of S plus P3, right? And all of that better equal some multiple of pi. Right? Okay, so that's all we have to check here, okay? So what we're going to first do is let's consider now certain regions here. So let's call this, let's start from maybe over here. I'm going to try to find another color that I haven't used already, and I think unfortunately we are out of colors. Tell you what, let's use green here, and I'll draw it. I don't want to draw right on the black, but I'm gonna, let's do it like this. Let's consider this region here. So consider this region. Right? So all I want to look at is S values that are in here, okay? So if that's the case, what we need to ask ourselves is we need to evaluate all of these terms over here, okay? So let's just maybe, to make this a little easier, let's write it over here. Maybe let me write a box, and I apologize, I'm not using the whiteboard space as ideally as I think we would like here. But what I want to do is let's ask ourselves a question: what are each terms? Maybe it is, yeah. What is each term in the region of interest? So in other words, I want to look at what is angle of S plus Z1, what is angle of S plus Z2, angle of S plus Z3, angle of S plus P1, angle of S plus P2, and angle of S plus P3. Okay? So let's just start going through it, right? And you remember now we can use these two rules that we just developed here, right? So angle of S plus Z1, where is Z1? Oh, actually crud. Z1 and Z2, we see that these are these pairs here, right? So we actually need to consider both of these two together. So let's go ahead and put these two sort of together. Maybe we should have written this, yeah, angle of s plus z1 plus the angle of s plus z2. I want to look at their sum together here, right? So we see that along this region, right, it's 0, right? Any complex 0 here, or actually complex pole, it's always 0. I don't care where you are, in what region, it's always 0. So this is just a big fat 0, right? Okay, let's look at angle of s plus z3 here. So the rule was, if the s location you're interested is to the right of the pole, its angle contribution is 0. Otherwise, it's pi. So this region right here is definitely to the right of 0, z3. So this is going to be 0, right? And we do the same thing for all these other poles, P1, P2, and P3. The region we're interested in are to the right of both P1, P2, and P3. So these are all 0, right? So you plug that in here, you get a 0 plus, well, actually, sorry, again, these two are sort of the mutant pair that go together here, right? Those turn into a 0. This is a 0 minus 0, 0, 0. Right? So what do you end up with? The right-hand side is just a big fat 0. 0 does not equal some multiple of pi. Right? So it fails. Any s location in this region does not satisfy the critical root locus angle equation. So this region is not on the root locus. It is infeasible for poles to be located there here. So this is a no-go, right? Let's just put this, I don't know, how about, let's put this as bad. Let's go bad, yeah, here, I'll just do it in green here, bad. Okay, so that region is not good. Let's move ourselves down to this next region between these two poles. Okay, so we're going to do the same thing here. So let's go ahead and now consider this region. Okay, and again, we're just going to reset our analysis. Okay, zeros. And we ask ourselves the same question. In this region, what's changed? Well, this is still 0, right? Z3, we're still to the right of Z3, so this is 0. We're still to the right of P1, this is 0. We're still to the right of P2, so this is 0. But aha, look at this. This is interesting. This region is actually to the left of pole P3. So angle of s plus P3, according to our rule earlier, it's actually pi or minus pi, however you want to look at it, right? So this is like pi. Right? Or minus pi. It really makes no difference here, right? I guess maybe in the rule we should have said you can make this plus or minus pi. Same thing. It's just some multiple of 180. Okay? So there we go. So let's just fill in this and check, right? So now we said that, all right, this is still 0. This is 0, 0, 0, and like minus pi or plus pi. Something like that. So we end up with this thing as basically the right-hand side is minus pi or plus pi, which actually is some multiple of pi. So yay, anything in that region satisfies this equation. So yes, this is good. This region is good. Maybe, so I'll fill this in with like kind of green. Because we're basically showing that this region of the root locus satisfies it. So yes, this is a valid region of the root locus. Let's just move on and down, right? So then you see the pattern at this point, right? Consider this region, right? You move it a little further, again, reset our analysis. Right? Okay, so again, these guys are always a big fat 0. We're still to the right of Z3, so that's 0. We are still to the right of P1, so this is 0. And now P2, but this, yeah, this region is what we're considering here, right? Now we are to the left of P2, so angle of s plus P2 is pi. And so we're still to the left of P3 here, right? The region of interest over here is to the left of it. So this is also pi. Great. So you get a 0, 0, 0, pi, pi. So the right-hand side comes down to like minus 2 pi, which actually is not a multiple of 1 pi here, right? There's no integer k that would make this work, so does not work. So this region is bad, right? So this is bad. Does not satisfy here, right? Okay, so now moving our way down, let's tell this region. And by now, I think you've seen the pattern here, right? Again, reset our analysis here, and you basically ask yourselves the same question. Does the S locations in that region satisfy our root locus equation? So again, this guy's a big fat 0. Z3, we are still 0. But now all these guys are pi, right? Because this region here is to the left of all of these poles here, right? So yay, we end up with a 0, 0, pi, pi, pi. So we get minus 3 pi, which, yes, indeed, is some multiple of negative pi here, right? So yay, this checks out, so awesome. We can go and fill this region in. So this is now good. And I'll fill this in with, okay. And lastly, the last region we have to consider here is this to infinity here. So now we're in this region. So again, reset all of our analysis. And you do it again, right? And we see, okay, 0. And now that region is to the left of frickin' everything. So you get a pi, 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 and pi, right? So this is 0 plus pi, 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 pi. So you have plus 1 pi minus, minus, minus. So I think this ends up with minus 2 pi, right? Which is not some multiple of 1 pi. So bad. This region does not satisfy the root locus here. So we end up with these regions here and here, which satisfy the root locus equation here that we said was so critical. So with this, you basically see the pattern that this again would work for poles or zeros. It doesn't matter as long as we are only considering regions of S which lie on the real axis. So this is the crux of rule number 3. You see that basically you get these alternating sections of valid, invalid, valid, invalid, valid, invalid, right? So what you do here is, if you look at this, and if we had just looked at only the poles that are on the real axis, and you just start numbering these things, starting from the right to the left, maybe I'll do this in a different color. Let's do it in black here. So let's call this is either pole or 0 number 1. It doesn't matter if it's a pole or a 0. And then you come here, pole 0 number 2. And then you could number these two if you want. They come in pairs. It's not going to matter. So for example, let's just do it for fun. Pole 0 number 3, and this is now pole 0 number 4. And then you get pole 0 number 5, and then pole 0 number 6. Okay? So if you look at that numbering scheme here, you see that the rule is valid regions of the root locus are to the left of odd numbered pole 0 pairs here, right? So to the left of 1 is valid here. And again, this is only, you only consider the ones on the real axis, right? Because it doesn't really make any sense to, like, what the heck does it mean to the left of this, right? This is not a valid region. So you only look at the pole zeros that are on the real axis here. And again, you just look for which ones are odd. So this one is, yeah, odd to the left is good. Here's an even number, so this is bad. Here's an odd number to the left is good. Even number bad here, right? So great. This yields our rule number 3. That maybe let me erase this and we'll write down our rule number 3 here. Okay, so rule 3 is basically that valid regions of the root locus on the real axis. So that part is critical, right? We are only considering valid regions on the real axis. So the valid regions are to the left of odd numbered poles / zeros. this is when you start counting / numbering from right to left. Right? So great, let's box this up. Here's rule number 3. Right? Okay, great. So again, give me a second to pause the video, erase the board, and we'll keep on moving on to rule number 4. Okay, so now we are on to rule 4. And this has to deal with what we're going to call the angle of asymptotes, as well as the centroid of the asymptotes. Okay? So to set the stage for this, maybe what we should do here is let's consider an example transfer function here. Again, let's just pick another one. Let's call this g as something like 2 over s plus 1 all over s plus 1 plus I, s plus 1 minus I. Something like this. Okay? And what I want to do now is we can start actually sketching a pretty reasonable root locus using our 3 rules here that we've developed so far. So rule 1, we see that there will be 2 lines / poles. All right, the number of poles is unchanged, so there's 2 open loop poles, there's still going to be 2 closed loop poles. So rule 2 here said that, okay, we have 2 poles and 1 0. So 1 pole will go to open loop 0, right? And 1 pole will go to 0 at infinity, right? And then rule 3, we saw was that valid regions on the real axis are to the left of odd numbered poles / zeros. So if we go ahead and sketch this thing out, right, let's go ahead and draw ourselves maybe a real imaginary axis and quickly look at the poles and zeros. So let me see, we got a 0 here at -1, and we got 2 poles at here and here. Sorry, wow, this red pen is not looking so hot. There, okay? So that's our system here. So let's see here. We know that, okay, applying rule 3 here, that the valid regions of the root locus are to the left of odd numbers as we go along. So we know that there should be a root locus branch here, kind of going all the way off to infinity. And we know that one of these poles has got to eventually end up here, and the other one has to go to infinity. So you know what, it's probably going to do something like, you know, both of these are going to come down. Maybe they'll meet here, and one of them is going to go this way, the other one is going to go the other way. So it's something like this. So you can see we're starting to get a reasonable behavior or understanding of how this root locus is going to behave just with these 3 rules. Now, this 4th rule here is dealing with this 1 pole or multiple poles that are shooting off to infinity. What we want to ask here is, what angle are they going to shoot off with? You know, I drew it like this where it's just flat, and that sort of makes sense, but how do we know that it doesn't shoot off at some angle like this or some other direction here, right? So we know that there are n minus m poles that go to zeros at infinity, right? So now what we got to ask ourselves is, what is the angle that these things shoot off at? Okay, so to answer that question, maybe what we can do here is let's consider, you know, an arbitrary example. So consider a pole 0 map of an open loop transfer function. Okay, so again, you know what? We could even use something that is very, very similar to what we just drew here. Okay, so here's your real, here's your imaginary axis. But what I want to do is I want to zoom in a little bit, or sorry, excuse me, zoom out a little bit. So again, let's take that picture and maybe, you know, you got something like this, and you got something here and here, something like that. But now what I want to consider here is, as some of these go to infinity, some of these S locations are going to be very, very far away from this. So like, let's choose like an S location way out here, right? And now what we want to ask ourselves here is we remember that the way root locus works is root locus is really talking about our good old friend, the angle equation here, right? So let's put our angle equation here. All it's asking about is where are all of the angles from each of these poles and zeros to these candidate S locations. And again, maybe to help ourselves remember how to do that, we can go grab our handy dandy friend here, our 4-step process, right? So what we need to do here is I need to look at the angle each one of these terms make when they contribute to the larger equation is basically draw a line from the pole or zero you're interested in to the S location you're interested in. And this angle, this is angle of S plus, I guess if we wanted to label these, maybe let's quickly label these. Let's call this P1, and down here is P2, and then here's Z1. And I guess these are all negative, right? This is, like we talked earlier, this is located in negative P1, negative P2, and negative Z1 here, right? So this here is angle of S plus P1, right? And then similarly, you draw a line from here to here, and this angle here is angle of S plus Z1, right? And then lastly, you draw another one here, and this is angle of S plus P2. Now, I think you get the picture, right? Is you can see as you go farther, if S, the S locations that you're considering are extremely far away from all these poles, like at infinity, all of these angles are effectively the same thing here, right? So let's call all of these angles, like, I don't know, let's call it phi A, how about? All of these are approximately the same angle, let's call it phi A, right? So it doesn't matter where all these poles are. They could be imaginary, complex, on the real axis, whatever. As long as you choose S locations that are sufficiently far away at an infinity, this is a completely valid assumption that all these angles look effectively like phi A. So if we write this down here and we actually think about expanding our root locus angle expression here, right? We can do that here, and we basically end up with, again, let's write this down for a couple of times. So that looks like angle of S plus Z1 plus angle of S plus Z2 plus yada 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 plus angle of S plus ZM minus angle of S plus P1 plus angle of S plus P2 plus, oh sorry, excuse me, these are minuses, minus angle of S plus Pn, oh sorry, I forgot the ellipses, minus dot 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 minus angle of S plus Pn has got to equal some multiple of pi. Right? Now what we see is all of these, every single one of these is basically phi A. This is phi A, 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 and this is phi A, if we are considering S locations at infinity and far, far away. So what we end up with here is you end up with phi A plus yada yada plus phi A minus phi A minus phi A minus da 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 minus phi A, and you get all these pluses show up. You see what? There's m of these, so this happens m times, right? And all of these minuses happen n times the number of poles, right? Is again equal to minus pi plus or minus 2 pi k, right? So we basically end up with, you could rewrite this thing as m phi A minus n phi A has got to equal some multiple of minus pi, right? Or I guess if you want to solve this for phi A, you could basically obtain this expression here. So phi A is, if you solve this thing, you would end up with minus pi plus or minus 2 pi k all over m minus n here, right? Where if you were to, again, simplify this here, you could get this thing to look like 1 plus or minus 2k times pi all over n minus m, right? So this, if you think about it, is an expression here for the angle of this asymptote, in the sense that as s gets far away, it has to always follow this angle, right? This comes out to be a constant number here. Now, the thing we should ask ourselves is how many asymptotes are there, okay? So let's come back over here and finish this, because maybe I was premature in boxing that expression, because we're not quite 100% done here, because we should ask ourselves how many asymptotes are there, right? So really, this is an equivalent question to asking how many zeros at infinity are there, right? And we know the answer to that. There are n minus m zeros at infinity. So in this example here, right, there are 2 poles and 1 0, and one of those lines are going to shoot off to infinity here, right? So basically what I'm getting at here is this indexing value of lowercase k here. If you think about this long enough, you got to make sure that there are only as many asymptotes as there are zeros at infinity here, right? So what we have to do here is we've got to be a little bit careful about the indexing here. So let's go ahead and consider this example right here. We see here that the answer here is one of these things should be here at an angle of pi, right? So phi a, we should have one of these angles and it should be at pi, right? Because that's the angle that this thing goes off with, right? So if you look at this here, in order to get that answer here, k has got to start from 0, right? When k is equal to 0, you basically get what? 1 plus 0. So you get 1, you get pi on the top, minus 2 minus 1. So you get, yeah, all right? So again, what I'm getting at here is, again, what we should write here is, let's write down the expression for phi a. So phi a was 1 plus or minus 2k times pi all over n minus m. And now we see that k, it starts at 0 here, right? And it goes up, you know, you go 1, 2, all the way up to, you don't actually go up to n minus m here, right? You got to subtract off 1. You got to go from n minus m minus 1 here, right? To take into account this zero-based indexing here, right? So you just want to make sure you don't run into the off by 1 error here when we're indexing the numbers, right? This is sometimes called the Star Wars error, right? Does everyone know why this is called the Star Wars error? When you're off by 1 here, when you're off by 1, right? That's this problem here, or your OB1. Get it? OB1? No? Does that make sense? Anyway, okay, now with that, I think we can box up this entire expression here. So this is a valid way to compute the angle of the asymptotes here, of how they shoot off here to infinity, okay? The other thing that maybe we'll state without proof here is that where all these asymptotes converge at is sometimes referred to as the centroids of the asymptotes. Let's just write this here, let's call it sigma a here. So this is the centroid of the asymptotes, and basically this is sum of all the location of the poles minus all of the location of zeros, all of this divided by n minus m here, okay? So it's basically, you can think of it sort of like as the center of gravity of where all of the pole and zero locations are. So the other expression for this, I guess if we want to be explicit, shoot, I'm running out of room. Let me move our little 4-step process. I think we don't need him right now. Okay. All right, so this is going to be sum of minus pk from from k equals 1 to n, minus the sum of negative zk, k going from 1 to m, all over n minus m. Okay, so this here, if we box the bottom one up, so both of these two equations together, the first one will give you the angle of the asymptotes, and this second equation for sigma a will give you where to sort of draw the convergence point of all of these asymptotes here. So this is basically example 4 here, or rule number 4 of how to calculate the angle of asymptotes, as well as calculating the center of mass of the asymptotes. So tell you what, let's go through an example of this here. And actually here, let's idiot check ourselves first with this one here. Let's make sure that we get an angle of 0 here. So plugging in our angle for the our expression for the angle of asymptotes here, right? We see that this is going to be 1 plus or minus 2k pi all over, what is n? N, there's 2 poles minus 1 pole, and we see k goes from 0 all the way up to n minus m minus 1. So it actually just goes to 0. So you plug in 0 for this, and yeah, we end up with this whole thing smashes down to pi. So great, that checks out. Let's check out maybe a more complicated expression here to see how this works, a more complicated example. Okay, so to get that more complicated example, let's go ahead and erase this to get ourselves a little bit of room. Okay, so where's our example here? Let's do something more complicated. So let's call this a G6. So this is going to be s plus 3 all over s plus 2, s plus 5 plus 2i, s plus 5 minus 2i, s minus 4. And again, just to be explicit here, right? This is our s plus p1, s plus p2, s plus p3. Oh, sorry. Whoops, no. Try that again. It's getting a little bit late in the evening. Sorry, z1. The zeros go on the top, the poles go on the bottom, right? p3, how many poles we got? 4, right? S plus p4, right? Okay, so in this case, we obviously see that, all right, we have z1 here of 3, which is basically a 0 at minus 3. And then you got a P1 value of 2, which is a pole at minus 2, right? That's this guy right here. You got P2, its value is 5 plus 2i. So here's your pole at minus 5 minus 2i. You got a P3 here of 5 minus 2i, meaning you got a pole at minus 5 plus 2i, right? You got to flip this, be very careful with all these negative signs here, right? Okay, so P4 is minus 4 here, which means you got a pole at positive 4, right? Okay, so we can quickly sketch this thing. So let's draw ourselves a real imaginary axis here. Okay, so let's just go ahead and plot this guy out. Okay, so you got a 0 here at minus 3. Let's just, here. Here is minus z1, okay? P1 here at minus 2. You got something right here. Here's minus P1. P2 here, you got this thing at minus 5 minus 2i. So here's P2. There's negative P2, I guess. And then its complex conjugate pair up here. This is minus P3. And then this guy, last one, is over here at positive 4. So here's minus P4. Okay, so that's the open loop poles and zeros. So let's go ahead and compute our angle of asymptotes and the centroid of asymptotes, okay? So the first thing we got to go ahead and check is, again, how many asymptotes are there going to be here? So there are going to be n minus m asymptotes, right? So there's going to be, what do we got? We got 4 minus 1, so there should be 3 asymptotes. Okay, so our expression for the angle here is phi a is going to be 1 plus or minus 2 pi k times pi all over 4 minus 1. And k is going to run from 0 all the way, 1 all the way up to n minus m minus 1 here. So it goes up to 2. So I guess, let's just do this. K goes from 0, 1, 2. That's how this works out. So all we got to do here is to make ourselves a little table here of k versus phi a. So k is going to go from 0, 1, 2. Okay, so you go here and you plug in k equals 0 to this whole big expression here. And what you'll end up with here is this is going to be pi over 3. Or I guess if you want this in degrees, that's 60 degrees. Okay? For k equals 1, you plug k equals 1 into this whole expression, you end up with, this is going to be pi, or I guess 180 degrees. And you plug k equals 2 into this expression here, and you're going to end up with 5 pi over 3, or 300 degrees. Okay, great. That's all of our angle of asymptotes. And now let's get ourselves the centroid of the asymptotes. Shoot, where am I? I'm running out of space here. Let's do it over here. Let's erase our little Star Wars error here. And try to just basically repeat this. So sigma A here, right? It's just summation of all of these terms over the number of zeros. So let's get this real clear here. So this is going to be negative P1, right? Minus P2, minus P3, minus P4, right? That's this term, minus negative Z1, right? Isn't that what we end up with? Okay, great. All of this, all over n was 4, that's 4 poles, minus 1. Okay, so now all you got to do is plug in all of these p values into here. Again, taking into account, being careful about the signs. Just to be, maybe to be completely explicitly careful about this, let's just write this out. So negative, what the heck was P1? P1 is this thing, 2. Negative 2 minus 5 plus 2i, right? Minus 5 minus 2i minus a negative 4, right? Minus negative, what is Z1? 3. There, all of that, all over 3, right? Let me just make sure I double check I got that right. This for, yeah, okay, so you crunch all these numbers here, right? And you end up with, this here is negative 5/3. Great. So if we come over here to our picture, I'll do this maybe in blue. Negative 5/3. Shoot, I should have labeled this. Negative 5/3, I think, is something like, what is P1? That's negative 2. So 5/3 is a little less than 2. Okay, so right here, around here is about sigma A. So that's the centroid of all of these asymptotes here, is right here. This is negative 5/3. Right? And now we see that they shoot off at angles of 60 degrees, 180 degrees, and 300. So 60 degrees is something like, I'm going to maybe butcher the hand sketch here, right? But this is one of these asymptotes here at phi A is equal to 60 degrees. Then you got another one at 180 degrees, like this, right? And you got another one here at 300 degrees. Right? So these are the asymptotes where the root locus is going to eventually go to here, right? So what might this start looking like if we really want to sketch this? So again, I'll use this green. Hopefully it shows up a little bit. Let me see if I can prime the pump a little bit. Okay, so let's start sketching this thing. So to the left of all the valid regions. So again, here to the left of all the odd numbered ones. So here is a valid region of the root locus. And then this is nothing, and then to the, wait, 1, 2, yeah, and then here's another valid region, like this. Okay, so what is this going to probably mean here? So look at these two poles. These two poles are probably going to come together. They're probably going to meet here in the middle here, and then they're going to break off. And they're probably, you know, based on these asymptotes, we know that eventually 3 of the poles have got to go to these locations here, right? So what that probably means is, I bet it does something like this, where this thing will approach the asymptote here, and then as you get far enough away, these guys are just going to start matching the asymptote here, right? And then similarly right here, what's going on here? Well, we know that this 0, right, this acts like one of these magnets here, so it's got to attract one of these two poles. So I bet these two poles do something like they come down maybe together. They eventually meet here on the real axis, and then one of them splits up and goes this direction, and the other one shoots off to follow this asymptote at 180 degrees here, right? So again, you can kind of see that with these 4 rules, we're really cooking with fire now here, right? Or cooking with gas. You can actually get a pretty reasonable understanding of what's going on here, okay? So again, rule number 4 here, maybe we should write it down just to be completely explicit, is basically the angle of asymptotes. So, shoot, I didn't arrange the board very well again, but basically let's just write it down. So rule 4 here is just the angle of asymptotes and the centroid of the asymptotes are basically what we just derived here, right? So here and here, right? That's rule number 4 here, is 2 ways to quickly compute where these asymptotes are located and what angles they shoot often. Okay, so let's pause the video. I'll erase the board and we'll get on to rule number 5. Okay, so here we are on to rule number 5, and this deals with sketching the angle of departure from a complex pole. Okay, so to set the stage for this, let's go ahead and again consider an example transfer function. I think let's call this G7. I think we're on to our 7th example function here. Let's make this guy look like an s plus 2 in the top here, and then down in the bottom an s plus 5 plus 3i, and an s plus 5 minus 3i. Okay, there we go. Okay, so the first thing we want to maybe do here is let's go ahead and draw ourselves a pole 0 map of this guy. All right, so we see that this guy has 1, 0 here at s is equal to minus 2. So here, let me see, minus 1, minus 2, minus 4, minus 5. Okay, and then let me just get a couple of axes here. Okay, so let's go ahead and write ourselves a 0 here, right? So here's negative z1 here, right? This is at minus 2, okay? Then we've got a pole here at the origin here. So here's minus p1, which is at 0. And then we got a pole here at minus 5 minus 3i. So that's over here, minus 3i, so something like this. So here's minus p2, which is minus 5 minus 3i. And then we got its complex conjugate way up here. So this is minus p3, which is minus 5 plus 3i. Okay, so that's our pole 0 map, okay? Now, what we want to go ahead and consider here when we're asking about the angle of departure here is we know from our previous rules here that these poles, all these poles, they're going to move here. Some of them are going to go to the zeros. Some of them are going to go to these asymptotes going towards zeros at infinity here, right? Now, with these poles here in the complex variety, the question is, which direction are they going to shoot off in first here? So what angle are they going to depart this location from? So, you know, are they going to go this down? Are they going to go straight over? Are they going to go up here? We just don't know which direction. That's what we would like to suss out right now. So what I want to suggest here is let's look at all these poles and let's think about where are they going to move as k goes from 0 to something infinitesimal, something very small. Well, I want to know, what is the root locus going to look like right at the beginning, okay? So this pole is pretty easy to understand here, right? This pole at negative p1, we know that from rule number, oh gosh, what number was that? Was that 3 or 2? We know the real axis here, this part to the left of the odd number is going to be the valid root locus. So we know this pole is headed to the left. So I'm going to maybe draw it, I don't know, something like this, right? Let's call this maybe like S1. Right? It's the pole location from where P1 started till where it just moved just a tiny bit, okay? And now, similarly for S2 and S3, you know, this pole, it's going to leave and move in some direction. I'm going to arbitrarily draw it, I don't know, maybe like this, okay? So here's S2. And similarly up here, let's draw something very close here. This is S3, okay? So the question is, we don't know where these S2 and this S3, those are the ones that we're actually very interested in, okay? I want to know which angle do they leave the original pole locations, all right? So to figure this out, we got to go back to our good old friend, the root locus angle equation, the thing that I keep referring to as equation 10 here, our good old-fashioned angle formula. And let's write this thing out for this particular situation, right? So for this situation, this looks like, all right, I got to sum all of the zeros. We don't have too many, right? So this is angle of s plus z1, right? That's that first term. That's super duper easy. Minus angle of s plus p1 plus angle of s plus p2. Sorry, a minus, right? Minus angle of s plus p3, right? Had better equal some multiple of pi, right? Okay, now this has to be true for any s. For any s that we would like to consider here on the root locus, it's got to satisfy this. Let's just choose this S3 here. Let's ask, where does S3 have to be in this complex plane to satisfy that equation? So in other words, what I mean here is I want S3. Let's put a subscript 3 on all of these just so we know which location we're focusing on, right? Okay, so now what we're assuming now is S3 is really, really close to P3 here, right? Because I'm looking at which angle did it depart. So K is like epsilon. K is like 10 to the minus 16. So it's really, really darn close to this. So we got to look at all of these terms. Angle of S3 plus Z1. So what is this term right here? Well, again, use our little handy dandy 4-step process, right? Right? That told us, okay, if I want to find out the angle of any of these things, all right, all I got to do is basically draw a vector from the 0 location, from Z1, to the location in question, which is S3 here. So in that case, let's look at this first term, angle of S3 plus Z1. So I got to find Z1. This is the pole in question, or sorry, the 0 in question, and I got to draw a vector to the S in question, which is up here. This is the angle, the S location I want to investigate. So that is like this, right? So this blue line is S3 plus Z1, the vector, right? And now the angle I'm looking for is this angle right here, right? So here is angle of S3 plus Z1. Right? Okay, so great. This isn't too bad to get now because from geometry, you can basically see here that, I guess this wasn't drawn exactly the best here, but because S3 is infinitesimally close to P3, I think you would all agree that I could sort of draw this vertical line that should come down through here at -5, right? So you can basically see here that this angle is inverse tangent of this x component and this y component here, right? So maybe let me explicitly write it out here because you can see the triangle, right? That's going to give me this angle. It's let's write it out here so I'm not skipping steps here. What did I do with the pen? Oh, here it is. Okay, so let's look at this first term here. So we can basically get here that, where did I put this? Okay, here. So let's do each one of these components one at a time here. So let me scoot over our little handy dandy plot so we can get a little bit more room. This is why this is nice that this is mobile. I can move this around the whiteboard. All right, so now let's consider each one of these terms, right? So consider each term, right? So here, angle of S3 plus Z1 here, right? This is basically an arctangent, right? An atan 2 or an arctangent. Now you got to, again, we got to be careful of which version of the 4-quadrant inverse tangent you're going to use here. Let's assume we're going to use a version where you pass it the x component first and then the y component. This is something like Mathematica, which is exactly opposite of MATLAB. So you got to be careful. In MATLAB, it wants you to flip this order. The first argument you give it in MATLAB is the y component. The second is the x. That's a software implementation issue. I think you all see what we're trying to get at. I just want to make it explicitly clear what we're doing here. So, okay, a tan 2 of what is the x component of this triangle? It's this distance right here, right? So you can see that it's 1, 2, 3. It's -3 is the value. But if you want to programmatically get that, right, what you would see here is this is... what is the, it's -5, right? Minus minus 2, right? That's the x component. So here's the x value that you end at, and here's the x value which you start at, right? So the ending minus the start will give you the proper x dimension here, or that proper x length here. And now the y is, where did you end here? That's up at 3 minus 0, right? Does everyone agree here? Okay, so if you go ahead and plug this in here, you would basically get that this is 135 degrees. Okay, great. Okay, so we got the first one. Let's go and get this next term here. I need now angle of S3 plus P1. What is that? Okay, so let's go ahead and come back over here and redraw our picture. So let me erase the blue. I don't need this blue line anymore. Okay, and sorry, I know this is going to be a little bit, this is going to get a little ugly. Let me see if I can do this cleanly without screwing too much up. So I kind of butchered some stuff. Let's redraw this so this is all looking halfway reasonable. Okay, so now, where is S3 plus P1? So let's use our little 4-step plan we got over here and get my blue pen. And I got to go find P1, right? So where's P1? P1's here. Here's P1, so I got to draw a line from P1 to S3. So P1 up to S3. Great, there we are. And again, you see it's just a different triangle, right? So this guy should have come down to here at -5, right? Maybe we should have labeled this, right? This is -1, -2, -3, -4, -5. This is 1, 2, 3, -1, -2, -3. There we go, right? Okay, so here we go. Let's just go ahead and find this. Here's the angle that we're looking for here, right? That is angle of S3 plus P1, right? So going through it again, you see, I already got the triangle set up. I just got to find the x component and the y component. So go ahead and a tan 2 this thing again. Again, give it the x and the y component. So this is a tan 2 of what's the x component? This is now -5 minus 0, right? And 3 minus 0, right? Okay, great. So you run those numbers, and where did I do? Okay, and this comes out to 149.04 degrees. Something like that, right? Approximately. Maybe I should say approximately. Great. Okay, so now let's keep going here. So I got these two terms. I now need angle of S3 plus P2. Okay, great. So let's go ahead and, again, erase all this. Okay, erase all the blue here because we can go ahead and try to identify the one we're looking for now. All right, let me clean up my picture a little bit here. Try to redraw it as much as possible. Okay. All right, following our 4-step plan, we got to find P2. Well, P2's down here. Lucky for us, this is going to be pretty easy here. So this, I draw from P2 up to S3, which is basically right there. Sorry for the hack job. You basically see it's 90 degrees here, right? I mean, but if you want to be completely formal about it here, you see that this is now a tan 2. The x component is 0, right? It's -5 minus -5, right? That's the change in x, and then the change in y here is a 3 minus -3 here. Something like that. This basically gets you 90 degrees, right? It's straight up, right? Because they're a complex conjugate pair, okay? And now, uh-oh, shoot, I didn't... Uh-oh, my computer decided to go to sleep. Hold on a second, I gotta go shake the mouse here to make this thing wake up. I was sitting here talking too long. Come on, there we go. Okay, now, the last term that we need here is this thing right here. Angle of S3 plus P3. And this is the catch here, right? Let's think about this. Erase all the blue. Okay, and let's come back and think, what is this? Angle of S3 plus P3, that's right here. I draw a line from P3 to S3, okay? And this angle now, right here, this is angle of S3 plus P3. if you think about this long enough, this is exactly the term that we're trying to solve for, right? This is the angle of departure of how does pole S3 leave pole P3 here, right? They're infinitesimally close to each other. The only thing is like, what is the angle of this infinitesimal closeness here, right? So this is actually what we're trying to solve for here. So you know what? Maybe we should just call this a value. Let's call this theta 3. This is what we're solving for here, right? This is the angle of departure of pole S3 from our pole at minus P3, right? This is what we're looking for. Okay, great. So we basically, this is perfect because this is now known, 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 unknown, known. So basically, just solve for this theta 3 here, all right? So what we end up with here is, let's just write solve for theta 3. Okay, what is angle of S3 plus Z1? We just figured that out, right? So this is 135 degrees minus S3 plus P1. Where is that? We just figured that out here. Okay, minus 149.04 degrees minus this one right here, S3 minus P2 plus P2. That's their 90-degree one, right? Minus 90 degrees minus theta 3, right? The thing we're looking for has got to equal, I guess now that we're all talking in degrees, this is 180 degrees plus or minus 360 degrees K, right? Okay, so you see, all you got to do is solve for theta 3 here, and you're basically done here. So in this case, we end up with a theta 3 of, what do we end up with? 75.96 degrees plus or minus 360 K, right? So this is awesome. So actually our picture there is halfway accurate here, right? So we see that the angle of departure, it does kind of go up in this direction, right? This is about, what do we say? It's about 76 degrees, right? That's the angle of departure here. And by symmetry, right, we could repeat the process for this S2 here, right? But we know that from symmetry, this angle that it's going to depart at right here, this is angle of S2 plus P2, right? This is going to be approximately, what, negative 76 degrees, right? Just from symmetry. Since they're complex conjugate pairs, they always have to stay complex conjugate pairs. So it's going to have the exact same angle. Well, it's going to have the negative angle of departure that its conjugate has, right? So this is pretty awesome. We can generalize this format, right? You saw that all this is doing here is you take our original governing root locus angle equation and you basically leave every term out except for the angle of departure from the complex pole here, and you basically isolate its solution here, all right? You isolate its angle, you will know every other term in this expression except for the angle that you're interested in, right? So the generalized form of this here is, maybe I'll write it up here where we've got a little bit of room here. Oh, actually, you know what? Now, let's take away a little four-step thing. Get ourselves a little bit more whiteboard space here. So the general form of this here is theta. Let's call it J here, right? Where J is the pole, the complex pole that you're interested in here. Okay. So this is going to look very darn similar to this, except you're going to have to move things around, right? So this is going to be generalized to be okay, this is going to be positive pi plus or minus 2 pi k plus, shoot, and actually, you know what, I'm going to run out of space. Let's move this up here. Let's scoot this over also. Let's write it right here. Okay, so here's the term here. So theta j here, right? So again, this is the thing you're solving for. This is angle of Sj plus Pj here. So in this case, Pj is the complex. This is the complex pole in question, right? And this is where we're trying to find, and this is the angle of departure here, right? And we saw that this is now going to be positive pi plus or minus 2 pi k, right? Plus, we're going to sum from I equals 1 to m all of the angles of S, sorry, not S. It's going to be pj plus zi, right? Minus sum from I equals 1 to n, but I cannot equal j, right? This is the one that you're leaving out here. Angle of pj plus pi. Okay? Great. Let's box this up and then let's talk our way through this thing real quick just to make sure we're all on the same page of how to read this, right? This is the generalized form of the process we just went through here, right? So again, left-hand side here, theta j is just another fancy word for this term, right? Angle of sj plus pj. So this is the angle of departure from complex pole pj here, right? And that's going to be equal to this term, right? You got positive pi plus minus 2 pi k, plus this term right here looks a little bit different here, right? This term is basically, I guess in this case we only had one term in here. There was 1 0 here. But if you had more than 1 0, you would sum up over all of them. And what we did here, right, is if you look at this, S3, we made the argument that S3 is basically P3 here, right? It's basically the exact same pole. So S3 and P3 are the same thing here, right? So that's why this is reflected as, this is the pole in question, right? PJ, right? This is the one that you're trying to depart from here. Okay, and then you just sum over all the zeros. And then it's the same story for summing over all of the poles here, right? So this summation term is these terms that I'm doing in red. It's these two terms, right? And again, same thing here, right? S3 is this green X right here is basically this red X of P3 here, right? So that's the PJ term, right? And the PI is all of the other poles that you're summing up over. You're summing the angle from P1 to P2, but you don't do the angle from P3 here, right? This is the key thing we got to make sure you don't miss. You leave one of them out, right? You leave out the pole that is the complex pole in question here, right? So again, J, maybe we should have added that here. Oh, no, we did here. Yeah, we said PJ is the complex pole in question here, right? So you sum over every other pole here, right? So just, I can't stress this enough, right? Let's just say, note, you sum over all poles except pole in question. And I guess if we want to be even more explicit, we could say except complex pole in question, right? So that's the one caveat to worry about here. But other than that, I think this is super helpful because, man, we can really sketch a real good root locus at this point. So for example, if you wanted to go through and compute yourself, if we wanted to flesh out that root locus of the example transfer function that we had here, we could go back and do a couple of our previous rules here, right? So for example, rule 4, if you went ahead and calculated the angle of the asymptotes, right? You just run through our expression for phi a here. And in this case, we know that there are 2 zeros at infinity, right? Because there's 3 poles and 1 0, so there's 2 excess poles here. So you would basically get 2 angles here. You would get 90 degrees and you would get 270 degrees, right? So if you found those two, these are the 2 angles you would get, and they're centroid of the asymptotes. If you went ahead and calculated using the expression we did before, you'd get here, you'd get -4, right? Okay, so let's go ahead and augment our picture here. So here's the centroid here at -4, and there's one asymptote that goes up at +90, and there's one other one that goes down at 270 degrees here. So we know that basically, well, here it looks like these 2 poles here, this one and this one, they're going to depart at an angle of 76 degrees and -76 degrees respectively, and they're going to approach these asymptotes. So you know what? I'd bet money that this thing looks something like this, and then it just starts going up until it starts approaching that asymptote, right? And similarly down here, this is going to come out at -76 degrees, and then it's just going to start approaching that asymptote, right? Okay, and then let's combine this with our previous rule, right? So rule number 3, which said valid solutions on the real axis are to the left of odd numbered poles. So that's just right here. So here's the only region that we've got here. So great, look at this here. You know, we've told 99% of the story here, where we see that this real pole, this pole on the real axis, will just go to this real 0 on the real axis, and these two complex poles are probably just going to shoot off to infinity along these asymptotes, right? So you get a lot of insight from just these 5 rules. So these 5 rules that we covered, like I said, deal with 99% of the fidelity that you probably need when hand sketching a root locus. If you really need more fidelity, maybe you should just be using a numerical tool to start with here. But that being said, what I think what I want to do now here is let's pause the camera, I'll erase the board, and maybe let's quickly touch on 5 more rules that could be helpful if you really care about it in that much detail. Okay, so before we move on to those, the last 5 rules, maybe let's summarize the core 5 rules that we just developed here. So let's just do a quick summary of the rules for the root locus, right? So just to refresh your memory, right, we went ahead and we first said we were going to consider an open loop transfer function, right, of the form g of s looks like some numerator polynomial over denominator polynomial here, right? So this was the output of the system over its individual input here. We'll look at those signals in just a second here. But again, we said that this thing looks like an alpha plus an s plus z1, s plus z2, yada, 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 s plus zm, right? All over an s plus p1, s plus p2, all the way s plus pn here, right? So this thing had m zeros and n poles, right? Or whoops, I guess we should have said number of poles, right? That's what n and m stood for, right? Okay, we made an assumption here that alpha was positive, and that what we wanted to do then was we said that under a specific feedback architecture here that looked like this, right? So here's your open loop system where you have u coming in and you have y coming out. We were going to look at a very specific architecture which looked like this, right? And what we were going to also then assume was that k was going to range from 0 to positive infinity. Right? That's the ranges of k's that we wanted to understand here, right? And if this was the scenario that we set up, we said that there were then 5 rules of how to sketch where the closed loop poles of the entire system went here, right? So what that did here was, again, you just look at the open loop transfer function and you develop these rules. So we said rule 1, number of poles is unchanged. Okay, so in this case here, the number of poles equals n here, right? And I guess maybe we should have made the other note here that we assume alpha is great, and we are then going to assume that n is greater than or equal to m. So we have a proper transfer function, right? That's how we derive these 5 rules. Okay, so that was rule number 1 here. Rule 2. We said that basically the closed loop poles start at the open loop poles and go to either one of 2 scenarios, right? So they are going to, they end at open loop zeros, right? So m of the poles will go here, right? And then the other scenario here is that they could end at zeros at infinity. And the remaining excess poles of n minus m poles go here, right? Okay, great. All right, perfect. And then what do we have for rule 3? So rule 3 was that valid regions on the real axis are to the left, right, of odd-numbered poles slash zeros. And again, you have to start numbering from right to left, right? Okay. What else do we have? Rule 4. We had the angle of asymptotes, right? For these zeros at infinity, we said that the angle of asymptotes, we call that phi a, was given by the expression 1 plus or minus 2k times pi all over n minus m here, and k ran from 0, 1, all the way up to n minus m minus 1 here, right? And then we said the centroid of the asymptotes, we call that sigma a, right, was given by summation from k equals 1 to n of minus pk minus summation from, k is equal to 1 to m of minus zk all over n minus m, okay? And then rule 5, shoot, I guess ran out of space. Let's come over here maybe. Hopefully we can fit this in here. So rule 5 was the angle of departure. From a complex pole, right? From one of these complex open loop poles here, right? And we said that this angle of departure from pole J, right? So theta J here, which we said this is the thing we're interested in, angle of Sj plus Pj, right? This is the angle we're interested in. You could compute that from using positive pi plus or minus 2 pi k, right? Plus sum from I equals 1 to m of angle of Pj minus, plus Zi, right? So you do all the zeros and then subtract off, maybe, shoot, I'm going to run into, I'll put it down here. Then you subtract from I equals 1 to n, but you don't do the pole in question. So I can't equal j. Angle of Pj plus Pi, right? Okay, so here on one page here, these are the 5 rules that we said will get you the majority of the behavior of the root locus here. And now there's another series of 5 more rules that might help if you really need to flesh this out. So I'll tell you what, let me pause the camera, I'll erase the board, and we'll get to those rules 6 through 10. All right, so if you really want to, we can delve into a few other rules, but we're going to do this very quickly. So rule 6 here is, I'm just going to say that you could also come up with an expression for the angle of arrival at complex zeros. So we just looked at how to calculate the angle of departure from a pair of complex poles. Well, you could also go ahead and find out what angle does the root locus enter those complex zeros at as k goes to infinity here. But in the interest of time, let's just write down that if you really want this, just Google it, right? It's not like Nike of just do it, just Google it here, because the reason I'm not going to spend any time talking about this is I literally have never come up with a scenario or never encountered a situation where I needed a root locus to be so precise that I needed to know what angle do the roots go into the complex zeros as k approaches infinity. If you're pushing k to infinity already, you've already done something wrong, right? You should maybe recheck your life and think about what have you done to get to that point here. So I'm just going to say that it's possible to derive this expression. We're not going to do it right now. If you go look it up, it's going to look a heck of a lot like the calculation for the angle of departure for complex poles here, right? But if you really wanted to, you could here. Here, rule 7, though, is a little bit more helpful here and a little useful here. This is the fact that the locus will break in or out on the real axis at 90 degrees. So if you have a situation where we've got ourselves poles or something like this, right? And you know that these two are going to come together, they're going to crash here, and then they're going to leave. Well, they're going to leave and they might do something like this, but initially when they break out from the real axis, this will be a 90-degree angle here, right? And similarly, if you have poles that come in, they might come in, but they will straighten out right before they hit the real axis and enter in or break in at 90 degrees here, right? So rule 7 is a little bit helpful. Okay, rule 8, this is a little bit of another kind of duh rule that maybe I don't even need to put up here, but for our root locuses, which are real here, and for real systems, you have complex roots coming in pairs, right? Right? They come in these complex conjugate pairs that are reflected over the real axis. So you're never going to the root locus for our systems, which have real controllers and real constants and real numbers in it, they will they'll always be symmetrical about the real axis, right? No matter how complicated they are. Okay, rule 9 here. So the root locus will not cross over itself. Right? So it's okay for the roots to come in here and crash into each other, but you're not going to have a situation where the root locus does something like this and crosses over itself, right? This will not happen, right? If you think about it long enough, what this is kind of saying here, that if this were able to occur, you're basically saying that there's a low value of K1, which will get you to this point. And then as you keep increasing K, you could find another K2 value, which is bigger than K1, which gets you to that same solution of the same roots here. So it's not a one-to-one mapping anymore between controller gain or root locus parameter K and pole locations if this were to occur. And since this doesn't occur, right, and that's not feasible, this is not going to happen. So you're never going to have the root locus crossing over itself. Rule 10 is a little bit interesting here, and let's just call this the number of lines rule. We already know from rule number 1, right, for a proper transfer function where there are more poles or the same number of poles as there are zeros, we know that the number of lines or the poles are not going to change here, right? However, if you're in a situation where you have potentially more zeros than poles, you are actually going to have more poles or more roots of the closed loop system than you started with here. So in other words, this here is a little bit, it might sound like a direct contradiction of rule 1, but remember, rules 1 through 5 were the situations that I said cover 99% of the scenarios, right, where you have a proper transfer function. This you might need to pull out if you have an improper transfer function, but it's basically an extension of this. So basically, let's just say that this rule states that there are at maximum n or m lines to the root locus here, right? So in the case where n was greater than or equal to m, right, this is basically just saying rule 1 here, right? So this is what we already talked about earlier, same and covered by all of our rules 1 through 5 that we talked about earlier, right? This is where you have a proper transfer function and everything is hunky-dory, right? But if you had more poles, or sorry, excuse me, more zeros than you have poles here, now what's interesting here is this is now you're in this rare scenario here, which really doesn't come up much, but maybe we will mention here that in the previous scenario, right, where everything was fine and dandy and there were more poles than there were zeros, some of those excess poles shot off to zeros at infinity here. Now, in this scenario, you're actually going to have more zeros than poles, and there's no such thing as excess poles. Instead, there are now poles that are going to come in from infinity here, right? So again, this is just something I wanted to bring up to your attention that is something to be aware of here. But to expand your mind, there are potential scenarios where you have more zeros than poles here. And in that case, in this rare scenario, you will have m, or the number of zeros, roots or lines on your closed loop root locus. Some of those poles are going to be coming in from infinity rather than shooting out to infinity here, right? Okay, so with that, I think this is a set of 10 pretty darn comprehensive rules that should get you through sketching pretty much any root locus that fits into the box that we just talked about here, okay? So to close out the discussion now, I think what would be useful here is let's erase the board and let's go through a more complicated, involved example that should hopefully stress the majority of these rules and put them to use. Okay, let's go ahead and look at a example that is somewhat more involved. So here we are. Let's go look at our 8th open loop transfer function of the discussion here. So this is going to be a s plus 1 plus I, s plus 1 minus I in the numerator here, and then s plus 3 plus 2I, s plus 3 minus 2I, s plus 2, s plus 1, s. Okay, here we go. So here's our open loop transfer function. Again, just to break this sucker down here, what do we got in terms of zeros here? We got a 0 here at s at minus 1 minus I. You've got s at minus 1 plus I here. So we got a complex pair of zeros here. Poles for the system, you have a pole here at s is equal to minus 3 minus 2I, at minus 3 plus 2I, and you've got one here at s is equal to minus 2, and s at minus 1, and s at 0, right? So we got 2 zeros and 5 poles. Right? Okay, so first things first, let's just go ahead and give ourselves a good bit of room here, and let's sketch out a root locus for this thing. Okay? All right, so we got our good old-fashioned real imaginary axis here. Let's maybe go units something like this. 1, 2, 3, 4, 5, 6 here. Okay, so negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, positive 1, positive 2. All right, then we got this going up to 1, 2, 3, 4. How about 1, 2, 3, 4? So there's 1, 2, 3, 4, and then minus 1, minus 2, minus 3, minus 4. Okay, all right, that's a reasonable setup. So let's just do a quick pole zero map and plot out all of these poles and zeros here. So starting off with the zeros, we got zeros here, here, that's it. And then we got poles here. Let's do the complex puppies first. So that's here, 3, 2. Okay, so it's here, and then here. Okay, and then you got a pole at minus 2, minus 1, and 0. Great. Okay, so here is what our open loop system looks like. Let's just start whipping through all of our rules and see what we end up with here. So, okay, rule 1. Num poles / lines is unchanged, right? So we have n equals 5 poles here. So there are still going to be 5 lines that we're going to have to trace out here for our system here, okay? So let's go ahead and do now rule 2, right? This is our talking about how many zeros at infinity, right? So we said the closed loop poles, right? What do? They start at open loop poles and go to, all right, let's see how many zeros we've got here. So there should be 2 of these, right? They're going to go to the 2 open loop zeros, and then how many zeros at infinity do we have? Right? We have n minus m, which is 5 minus 2, so we should have three zeros at infinity. So there should be three asymptotes that are going to shoot off here. So, all right, why don't we go ahead and deal with rule 3 here. What was rule 3? Rule 3, this was the valid regions of the real axis. Okay, so we can quickly sketch that out. We said that the valid regions of the real axis are to the left of odd numbered poles or zeros. So here we go. Here, odd, so yep, let's just do this. This is pole 1, 2, this is not. 3, this is. So yeah, wow, this entire section over here is actually a valid part of the root locus. So it's just going to do something like this. Off to infinity. There we go. Okay. There we go. So rule 3 got us all of the root locus locations on the real axis. All right. Rule 4 was our asymptotes. Right? So we said, shoot, I wonder if I'm going to have enough room for this. Tell you what here. Yeah, you know what? I think we'll make it fit here. Okay, so phi a, right? We said that this was 1 plus or minus 2k times pi over n minus m here. And k is going to go from 0, 1, all the way up to n minus m minus 1 here. So up to 3 here, because we said that there are 3 zeros at infinity, so there should be 3 asymptotes. So you plug this in here, and you're going to get phi a is going to be 60 degrees, 180 degrees, and 300 degrees. Okay, and then if you go ahead and compute the centroid of all the asymptotes, and actually, yeah, now we ran out of room. Now let's come over here and get rid of some of this. Shoot, I wonder if I want to. Okay, tell you what, let's erase this. I think we want some of these numbers still up here. Okay, so here's our centroid of the asymptotes, sigma a here, right? Which was sum from k equals 1 to 5, right, of minus pk, minus sum from 1 to 2 of minus zk, all over n minus m, 5 minus 2. Okay? So, all right, if you start plugging this in, I guess maybe just again to be explicit here, let's do all of these here. So this is going to be minus P1, minus P2, minus P3, minus P4, minus P5, minus, and then what I guess we got to do is, let's put this in brackets. The sum here, this is minus Z1 minus Z2, right? All over 5 minus 2. Okay, so now we just got to plug in all the values for P1, P2, P3, P4, etc. here. So, I'll tell you what, let's do this over here so I don't cram all the space. Let's just do it right next to it. Okay. All right, so this would be something like minus 3 plus 2i minus, hold on a second. Yeah, minus 3 minus 2i. Okay. Minus 2 minus 1 minus 0. Okay, that's all those first ones. Minus, and then the term we had in brackets here, this is minus, okay, what is Z1 here? Z1, this is going to be 1 plus I, right? And then minus 1 minus I. Great, all of that over 3. Okay, so again, crunch all of these numbers, and what you should end up with here is minus 11 thirds, or minus 3.67-ish. Okay, so great. With this information, we've got ourselves the centroid of the asymptotes. We've got the angles here, so let's just go ahead and plot those out in blue. So the centroid should be somewhere around here. Here's sigma A, the centroid of all the asymptotes, and we got angles going off at 60 degrees, 180, and 300. So there's going to be some asymptote like this, and then this, and this. Right, so those are our three asymptotes. Okay, all right, now let's go ahead and do rule 5 so we can figure out the angle of departure of these complex conjugate pairs here, these two right here. So let me go ahead and erase this. We'll get a little bit more space. Okay, so rule 5, right? Rule 5 was our angle of departure. Right? Okay, so the angle of departure, theta j here, right, which was angle of Sj plus Pj. This is the angle that I'm interested in. If we consider this to be maybe Pj, right? Maybe let's first consider that top one here. So this is equal to pi plus or minus 2 pi k, right? Plus summation from I equals 1 to m of angle of Pj plus Zi, right? Minus summation from I equals 1 to n, but you skip the pole in question, angle of Pj plus Pi, right? Okay, so let's go ahead and just call this Pj, I don't know, let's call it P1, how about? Maybe to make our lives easier. Let's call this thing P1. Okay, so this is the one that we're interested in. Okay, so then in that case, expanding this here, we see for us, we want j is equal to 1, right? This is the pole in question. Okay, so, all right, theta 1 here, right? The angle of departure from pole 1 here is just going to be, well, expanding that guy out, we're going to get pi plus or minus 2 pi k. Plus, let's go put let's do this first summation maybe in this square bracket, right? So this is angle of P1 plus Z1 plus angle of P1 plus Z2, right? Okay, there's that first summation up here. Now let's do the minus summation. So this is all now minus, and then let's put this in brackets. Angle of P1 plus P2 plus angle of P1 plus P3. Oh yeah, 1, 2, 3, right? Plus angle of P1 plus P4 plus angle of P1 plus P5. Right? Because we skipped I is equal to 1, right? So there's no, yeah. There we go. Okay, so again, all we see is we just got to go ahead and grab all of these terms here. So again, what I think would be helpful is our little 4-step process that we developed earlier. Let's just slap it on here. Well, actually, sorry. Let's slap it somewhere else because this is exactly what we're looking at, is this root locus plot here. So maybe let's slap this on here. Right? Here's the procedure to get all of these angles of these quantities. Right? So let's just do 1 or 2 of them, and again, we'll get the pattern here. Let's identify this one here. So let's first focus on this term here. Angle of P1 plus Z1 here. Okay, so all that means here is I got to go find myself Z1. Crud, and I guess we didn't label these here. So tell you what, let's number all these just so we're all on the same page. Let's call this Z1, Z2. We already got a P1. Let's call this, how about P2? P3, P4, and P5. Okay, all right, there we go. We got all these labeled here. So now all I got to do here is to get angle of P1 plus Z1. I go to Z1, which is here, and I draw a line from Z1 to the other S location in question, which is actually at P1, which is over here. So here we go. Let's just draw this. There we go. So here is the vector P1 plus Z1. So here's the associated angle from the horizontal, right? Okay, so this thing is angle of P1 plus Z1, right? So we go through our discussion here where we see that, okay, all this is here's the triangle that's relevant. Right? Okay, so to programmatically write that down here, this first term here of angle of P1 plus Z1 is going to be A tan 2. And again, let's assume you give it the x component and then the y component, like Mathematica style here. So this is going to be A tan 2 of, what's the x component here? So the x component here is, let me see, well, I guess it's just -2 here, right? -2, so you go 2 units in the negative x direction, and you go 1 unit in the positive direction, in the positive y direction, something like that. Great. Okay, and if you plug this in, you get, this is about 153.4 degrees, right? And you repeat this process for all these terms. And for the completeness here, and just for the lack of, in the interest of time, let me just write out the answers and I'll let you verify them yourself here, right? So P1 plus Z2. So this is the same thing, except now you're going to draw a line from Z2 up there. And you see that doesn't change a whole ton here, right? So this is A tan 2, again, of XY is going to be A tan 2 of, the x component is the same, right? But the y component is now +3. So this gets you an answer of 123.7 degrees. Okay, and then angle of P1 plus P2, right, is now, where's P2? It is, oh, it's here. Okay, we're going to see this is basically a 90-degree angle, right? Because it's coming from here up to P1, right? So this is, again, just to make this all nice and clean and uniform here, this is going to be A tan 2 of 0 and 4, right? Yep, okay, so this gets you 90 degrees. Okay, and then angle of P1 plus P2 is going to be A tan 2. XY is A tan 2 of, okay, so what's the x component here of P, oh, sorry, this should be a P3. Okay, P3, so P3 is over here. Okay, so the x component is -1, and the y component is 2, right? So this here is going to get you 116.6 degrees. Okay, and then angle of P1 plus P4 is A tan 2 of XY, A tan 2 of, okay, where is P4? It's over here. So, okay, so we got an x component of -2 and a y component of +2. So this is going to get you 135 degrees exactly. And finally, the last term we're looking for is angle of P1 plus P5 is going to be A tan 2 XY and A tan 2. Okay, so the x component, where's P5? It's over here, so the x component is now 1, 2, 3. So we got -3 and +2 in the y direction. And this gets you 146.3 degrees. Great, so now you plug all this into our expression out here, and we end up with la-di-da, where I ran out of space. Okay, here, tell you what, let's get rid of this because we don't need our little 4-step process. We just used it a ton. So voila, the magical answer you get here for θ1 is, what did I get here? Oh, -30.75 degrees. Okay, so let's erase some of these other extraneous blue lines that we don't need here. I apologize for the lack of colors here, which is kind of probably making this a little bit busy. Okay, because I want to leave the blue line, which represents the asymptotes. I want to kind of erase the others. Okay, redraw. All right, so we know here that the angle of departure from this pole is actually -30 degrees here. So that's kind of fascinating here. So actually, it actually goes down, something like this. So here, this should be -30.75 degrees here, right? And then by symmetry, this angle of departure here should actually be +30 degrees, so something like this. So that's interesting. They're going to kind of go off initially like this, almost like toward these asymptotes here. So with all of this, I think we're in a real good location to kind of sketch where these two poles are going to go. So we know that this pole is going to come down at minus 30.75 degrees initially, but then it's probably going to even out and approach this asymptote. Something like this. Similarly here, this is going to come up at 30 degrees, but then it's going to probably bend down. And again, maybe this isn't drawn to scale exactly, but this gives you a rough idea here, right? So here we go. I'll try to darken these up. I know the green doesn't show up the best on the camera, so I'll try to make these things a little bit fatter so we can kind of see. But you can see that in just a couple of minutes, we're able to sketch out a very robust root locus. So you kind of see what's going on here, right? We see that these two actually, sorry, wait a second. We're not done yet here. Yeah, what did we do with these two? These two come together here, right? And now we could almost use, what was it, rule 7 here that says these two, when they come together, they're going to break away at 90 degrees. So this is probably going to come up and down here, right? And we know that they're going to get sucked towards the open loop zeros here, right? So eventually, as I push K hard enough, these things are going to probably have to go to these zeros. If we really wanted to, you probably could see what angle do they come into these zeros at? What is the angle of arrival? But I'm going to just do some artistic sketching because you really are never going to come into a situation, I think, where you need that level of fidelity here. But again, here we go. Look at this. With just applying a few of these rules here, we get a very good understanding of the system. So you get a good physical intuition that you know, for this system, for example, you can't use an arbitrarily high gain K. If you notice these two poles, P1 and P2, eventually they're going to cross the right half plane, and you could wind up into trouble here. So this is really powerful here, right? Understanding how the root locus is going to behave from a fundamental concepts perspective is very, very useful in control design here, as we're going to see in the future. So that being said, you know, we spent a lot of time developing these rules, talking about how to sketch them. I think the thing that was probably nagging you in the back of your head now is thinking, you know what, sure, you sketched all these here, but how do I know that they're actually right? I should probably run over to some computer numerical tool that will allow me to validate this. And I hope that's what you're interested in, because that's exactly what I want to talk about next, is how can we use MATLAB and other tools to give it a root locus, or excuse me, give it an open loop transfer function and an arbitrary system architecture, and have it compute a root locus for us. So that's our next discussion here, and this is actually going to be a multi-part discussion on root locus, as you're going to see, because once we understand both how to sketch this as well as how to use some numerical tools, we can really start thinking about designing controllers, either PIDs, PI, lead, lag, other different types of controllers using this type of root locus scheme here. So with that being said, I hope you enjoyed the video here. I know it was a bit of a longer one, but I hope it was worth it, because this is as we've said, is very, very important. So if you liked it, please subscribe to the channel here. We're going to have a lot more discussions here on root locus. Let me know what you think about this video here in the comments, or if there's other topics you'd like to see in the future. I'd love to hear from you. So with that being said, I hope to catch you at one of these future videos. Until then, I'll talk to you later. Bye.